our agenda. So I'm going to start with like Steve was discovered by citizen scientist, our photographer. So we have a special guest today that is Neil Steller that is going to tell us a little bit of the story and show us some of his amazing photographs.
Awesome.
But also at the beginning, we knew very little, and one of the first results was the association between Steve and a very narrow and strong subauroral ion drift. So right. This is based on one event. So today we're going to hear about more events from Bill Archer, where he will talk about Steve being the ionospheric manifestation of SCIDs. And then we will go to Carlos Martinez, who will tell us about the relationship between Steve and maybe SAR arcs. We will hear from Phil Erickson and the contributions from Millstone Hill to Steve. And then Gareth Perry will talk about radar measurements of Steve. In general, we also did some one study event that showed us that Steve was not associated with particle precipitation, so it will not form as an aurora, and more evidence of this we probably will see from Megan Gillis that will show us,
Oops, sorry.
Radar measurements of Steve.
Yeah.
Oh, I'm hearing myself. That's what I'm hearing.
Sorry, I forgot to switch off the audio on the YouTube live stream and it went live. Sorry. Yeah, I think it should stop.
No problem. And then I'm going to mention that Megan is doing this, and then Brian and Toshi will also show us probably some picket fence characteristic. That's the secondary structure that sometimes is observed with Steve. And Josh Semeter is also going to tell us a little bit more details about this picket fence structure. And then finally, last but not least, we will have Liz McDonald talking about historic citizen scientist observations of Steve. That's Kat. That is Kat. Is Kat in all of them? Yes, of course.
Could you also brief, I think you mentioned it in your slides. Could you, okay, yeah, it's right there in the slide. Could you also mention, if you don't mind, submit questions via chat or?
Yeah, so that will be my very last sentence that I'm going to say. And if you have any question during the presentation, please feel free to add it to the chat or in the chat using YouTube.
Awesome.
And I can see the YouTube streaming right now.
And I enable the chat.
Yeah, I see it now.
All right, awesome.
There. But it will be like a minute I'm going to talk. I'm not going to talk more than that. It's just to to give an overview.
Yeah. And hopefully Carlos has got enough time to switch back from the other session.
All right. If not, we put Phil first and then Carlos. So
yeah.
As soon as the technology doesn't betray us, I think we will be fine.
No, I think it looks like we're in decent shape, so hopefully we should be fine. Yeah.
I think this is fine now. Yeah. Let me put full screen. So you should be seeing the full screen now.
Yes. Yes, I do.
Perfect.
All right.
I'm just hoping speakers will not use my link and they will use your link.
No, it's just the speaker. So, and we've corrected it. Not corrected.
Thank you. I'm sorry.
No, absolutely not. No, it's easier for me because I can just pick it off my account. Otherwise, it's so easy to, lose that thing.
Use one of the test ones like I did. I'm just making sure I don't have any message from any of the speakers. So yeah, we just have half an hour. I have an email. Oh, Liz shared the slide, so I'm going to save it to Okay. You see my mouse if I move it? I want to, yeah, okay, perfect. So we can use this as a pointer.
Hi, Bea. Hi, Fahad.
Hi, Megan.
Nice to meet you.
Hi, Megan. Nice meeting you.
Do you want to test your slides?
Yeah, I'll see if this works.
Let me stop sharing.
Okay, hang on. Hang on.
Oh,
Oh, here we go. Here we go. Hang on. So, oh, you're on screen too. Okay. Share this. I'm just going to
okay, perfect.
move that.
Perfect.
You see stuff?
Yes.
Hopefully just my presentation. Oh.
Yeah, I only see your first slide, so.
Okay. Oops. There.
Looks perfect.
Okay.
Awesome. It worked.
Perfect.
And if not, I have all the presentations open, so we can just hop on my screen and then we will share. Marat or I will share. By the way, Bharat, am I pronouncing your name correctly?
Yes, yeah.
Okay.
Yeah.
Bharat?
Bharat?
Bharat, okay.
I
Sorry.
wasn't. I should have asked this like about 6 months ago, so I'm really sorry.
No, no. You're doing it right. So
Thank you. I'm glad. Awesome.
I'm also going to record the video. It should go into my local thing, but I'll do it when we start. But the YouTube stream is live now, so we should be good.
The YouTube is streaming, and we have 4 likes already, so I'm happy about that.
Yeah.
Oh, 5 likes. Do you want to stop sharing? No. Perfect. Thank you. And then I'll share the intro slide. That is this one. It's for now, because if anyone wants to test the slides,
yep,
I'll stop doing it. So it's just to make them know they're in the correct session.
Hey, Bia.
Yes.
It looks like Neil's in the other session. I'm getting an email that he's in the 994 session. Could you text him the updated one? I'll send him an email.
Okay, yes, I will immediately. I'll actually, I think I have his, let me, perfect. I will immediately. Okay, I email him, and I'm going to text him too. Yeah.
Afternoon, everybody.
Hello, Gareth.
Hey,
Good
Gareth.
to see you.
A lot of people on already.
Yeah, I'm excited.
So my affiliation is University of Saskatchewan. not University of Saskatoon.
I always make a mistake. Thank you for letting me know. Let me stop sharing. Thank you, Bill. It's good to see
That's
you
awesome.
too.
Yeah, Rob just
What am I?
texted me that.
Thank you, guys. I was trying to get away with the easier word, but not really. And now that I'm writing it, for sure I'm going to have a typo. Okay. To delete these. Thank you.
All Canadians grow up pronouncing Saskatchewan very strangely in their head just so that they can remember how to spell it.
You Canadians have superpowers that Chileans do not.
We're
Okay.
talking about Saskatchewan.
Yeah.
Easy to draw, hard to spell.
Oh my God. I was going to put you Sask, and then I said, no, let's put the whole thing as you have let it.
You can just say U of S. It's fine.
But not everyone knows what U of S is.
Right.
So the only problem is
Nice to meet you. I'd say hi. Hear about you a lot, but I've never actually met you. Hi, Brian.
Hi.
Hey, everyone.
hello.
Hello.
Thank you guys for connecting. I'm fixing my slides.
Yeah, I just finished mine.
Okay.
Does the picture in the back off center? Does that bother people? Yes?
It's really nice. No, it doesn't bother. No, it looks really nice though.
The local artist. That's actually it's off a photograph that I took in California on a beach. It's me, my wife, and son leaping, and a local artist interpreted it. We're the three bears in there. Actually, it's quite cute.
I love the
Is it
bear.
acrylics or oil? Looks like
Oil
acrylic.
paints.
Oil. Okay.
Yeah, it's Mandy Stobo in Calgary here. She does amazing work.
I believe I went to high school with Mandy.
You
Really?
did?
Yeah, if she's roughly in her mid-30s, then I imagine there's that many Amanda Stobos running around.
Yeah, I've never known her as Amanda though. So yeah. What school did you go to?
Went to Cochrane.
Okay.
So I've actually been meaning to ask Neil. So your Zellers, these Zellers are they Saskatchewan, to your knowledge?
Sorry, say one more time.
So the Zeller name, does it come from Saskatchewan Zellers?
Yes, my great grandfather split off from the Wisconsin Zellers and moved to St. Walburg, Saskatchewan, and kind of started the Canadian version of us.
I see. Yeah, because so I have Zellers in my wife's family.
Oh boy,
great grandparents. Yeah, that's right. We're part of the Zellers that then decided that Saskatchewan had something in the water and moved to Calgary.
Yeah, I've been here 23 years myself. Where's everybody else calling in from?
Hi, Phil.
Hey, B.
Good
How are you?
Good. How are you? I love your background.
Oh, that's Haystack last fall. We had a double set of cloud fronts go through at sunset.
That's beautiful.
Yeah. Nothing professional, Neil. Just me wandering around. Yeah, I'm in Eastern Massachusetts. I would be in an observatory, but I'm home.
I would be on a boat on the Mackenzie River Delta, exiting the river, going onto the Arctic Ocean to go to Tuktoyaktuk today, hosting 6 photographers on this tour today. Right now, at this moment, here I am. I'm glad to be here, though.
Yeah, life is funny.
Yeah, it's hilarious.
Hello, everybody.
Liz can't get into the thing right now. She's trying to chat.
I'm in.
Oh.
Oh, there she is.
Liz.
Hi. I wonder if there's a way to get in without the web version of Zoom, because I have audio issues sometimes with the web version.
There's a phone app, isn't there?
There's also a desktop app if you're using Mac or Ubuntu.
No, I just want to use the regular Zoom.
The regular client?
Actually, ask the one that is presenting for the slides, Bharat and I, because of the NASA.
Right.
Sorry, I can't hear you guys very well.
Because if you have problems, Liz, I can share your slides.
Excuse me, Liz. I've found trouble if I log in, if I try and use Zoom through BU. This is Steve Smith. So what I do is I downloaded just the bare app, the Zoom app from the site, from the Zoom site, and installed that, and then just put in the little meeting ID number in that, separate from a web thing, just as a bare app. And
that's what I want to do, but I'm not sure what the meeting ID number is.
It's in the if you look in that PDF that had the connection information. It's in there.
I can also read it to you, Liz, if you want. I've got it on the screen.
That would be fabulous. I'm sorry, I did not see a PDF.
No, that's okay. Here if you got a pencil, 950. Okay, 950. 8606 3279.
Okay, I think I got that, and I think I will try and log in that way if that's
Yeah, and I don't know if there's a password, but
there shouldn't be any password.
Okay.
Yeah.
Great. Thank you, guys. Sorry.
No problem.
And we can share your slides if you have any problems, so don't worry about it.
You can't share mine. I added a bunch since I sent them.
Uh-oh.
Do you want to test your slides?
Yes, I do.
Okay. Perfect.
And I can start it, right? It's not a spelling error, by the way.
Yes, it works.
It works. Everybody can see that.
Yep.
The photon arc is not a spelling error. It's all part of it. Because I'm a dummy.
I think the word whatever, I'd love to have used that in a presentation. I have not yet to date, but now I will.
This is my first 4 Cedars that I've used whatever. So there's 100%.
That's great. That's actually great.
Okay, getting out.
Yes, you are.
Can you guys hear
Right
me
over
now?
the top is it?
We can hear you, Liz. Is that better?
It's better for me. Thank you.
Yeah, actually, you were kind of freezing a few times before, and you don't seem to be now, so that's good.
So I have my notes stacked up on blankets behind my camera. Anybody else?
Mine are in front of me, so I'll be reading down.
I'm gonna try. Well, I'm speaking in my. Well, I guess I come up, but yeah. So if I look like this, does it look weird?
Whatever.
2 points for you.
Oh, that's awful of me. Sorry.
That was amazing. I feel like part of the team now.
You are. Are you kidding?
Yeah.
I have lens and camera envy now, so.
I speak about that actually today.
Oh, that's good.
A little bit, yeah, kind of like that. FOMO.
That's right.
6 more minutes.
So who's the moderator for the questions and stuff? Who's set up to do that, or is
the idea is that we take turns. So if you want to jump in, because probably Bharat and I will be trying to switch slides and call the speakers and move questions. So the questions are going to be asked on the chat for Zoom and also in YouTube. So I'm going to be pasting questions from YouTube to Zoom.
Okay.
So whoever is reading them, they can see them.
All right, so I have the window open then, and I will just sort of monitor that.
That would be awesome.
Yeah, no, and you're entirely right. You have to get somebody devoted to that. I've tried to do both before. It does not work. You just can't pay attention to three things at once. Yeah, sure. So I'll do that then.
Thank you.
Sure.
It's a really good idea. You guys have the YouTube going as well. I know we hit capacity this morning in the rocket session. So they were at 100
Wow.
and people couldn't get in and they didn't have a backup. So
we actually share with the Alberta Aurora Chasers the YouTube link because that is a little bit more stable for them to just jump in and watch that and put the questions there. So that's why we did it.
That's a good idea.
That was Barat. He's a genius.
Everything's because of the Alberta Aurora Chasers, isn't it?
Well, that's right. That's how we know we're at the big time. You guys are here.
We haven't had Aurora for months. It's terrible right now.
I feel your pain.
Thanks.
But you got hail.
Yeah, we got a hail. We had $1 billion of damage in 3 neighborhoods in Calgary last week. $1 billion. It came down like grapefruits like this.
Oh my God.
Like, I didn't know siding could do that.
It just shredded. It shredded the siding like paper. Like it was crazy.
Oh.
Hi, June.
Ouch.
Yeah, I think there's been various points in time where Calgary has had the most expensive natural disasters per unit time, just because you'd get like 2 minutes of hail making an incredible amount of damage.
Cars floated away in the hail this time. It was crazy. Yeah. But we don't have anything else to talk about in Calgary, so.
I don't know if I believe that, but
Yeah. We don't have weather. We have nothing.
You always have the discussions of oil.
No, we don't. It's a sore spot right now.
I know. That's why I said it.
I don't know why our gas costs $1 a liter right now. It makes me crazy.
Oof.
I know.
Wow,
That's $4. That's $4 a gallon, by the way.
yeah, that's a factor of 2 more than down here in the States. Huh.
I know.
Hello guys, Carlos here. Can you hear me?
Yes.
Hello, Carlos. You're a little tinny. You might want to move a little closer to the microphone, but we can hear you.
Okay. I tried to reduce the number of my slides, but I think I will leave you just with 2 minutes, Phil. Is that okay?
Thanks a lot.
Yeah, I thought about you. Just kidding.
Yeah. Of course you did. I'm prepared to skip almost everything I have, so don't worry.
Good stuff
there.
there.
Because I figured out you'd go over. That's...
Oh, what do you mean?
I'm pretty happy because I'm not going to steal anyone's thunder.
No, you're not.
Oh, can anybody hear me?
Yes.
Okay, yeah, good.
Neil, you're just going to make all our slides look boring and not that pretty.
That was my goal from the beginning when you asked me. So.
Yep.
I reset my modem just for this. Just this is important to me. So
Yeah.
just so you know. Well, my son's upstairs actually. He's 12 years old. He's on his last day of school, and they have 2 full hours on their Zooms today. So the both of us are competing for bandwidth right now, but we should be fine.
Wow.
Hi, Bennett.
Hello.
Oh, I don't see him.
There was a request for a Bennett flyby.
He's sitting. He's not like.
Ghost Rider, the pattern is
Couldn't
full.
resist. I love seeing him. He's so big now.
We have audience of all ages.
Yeah.
Those early career scientists are getting younger and younger.
hope the funding is following suit.
It's 3. Should we wait like 2 minutes to start, or should we start immediately?
Looks like we've got 62 people according to the
my
window
God.
at the bottom, so that's pretty good.
And there are 23 on YouTube.
Yeah.
The concert session just wrapped up, so it might take people a minute to figure out the new link for Zoom. So
Oh,
trickle in as that wraps up.
right.
I can sing
Hi,
a song
Bruce.
to start just to let them in.
Are you guys recording this session? Or you already are with YouTube? Okay, so all right.
Yeah.
Awesome. I always forget to record, so.
Thank you.
Me too.
So now, hello.
Hi, Evgeny.
Hi,
Good to see
Evgeny.
you.
Hi, guys. Good to see that you are healthy.
Likewise.
Yeah.
Yep. I agree. All right.
Hi, Phil. How you doing?
Oh, hello, John. We're hanging in there in the strange world we find ourselves in.
Right. Right. Terminate my dream of attending Cedar meeting in person.
Yeah, that's well. You're still here.
I'm still here, yes, but who would have thought?
Well, better than not having it at all. That's my thought.
In some ways, it's actually better than in previous years.
There are interesting things. That's right.
Well, sure. And some people don't usually come to Cedar can drop in for a few of these sessions.
Yes, Bob. Hello.
This year, yeah.
Hi, Bob.
Hello, everyone.
Bob, hi.
Might as well.
What do you think, Bea? We've got a few more people. There's probably about 10 or 15 more people that have shown up.
Yeah, I think we can start because I have 3 slides that is a very general introduction with the speaker, so we can start. Yeah. Okay, so we start. Welcome everyone to Cedar 2020. This is the Subauroral Science, Steve Sub's SAIDs and SAR ARC session. So I have the list of the talks here to your right, and we have a large variety with amazing speakers that I want to thank for being so nice to present in our session. So the idea of this session is to review some of the Subauroral science that is relatively new, and it was kind of awakened by this new discovery of Steve, in which we saw that some of the things that we knew are a little bit unknown right now again. So as a very general thing, Steve was discovered by citizen scientists, amazing aurora chasers that take pictures of the aurora at night. And this image over here is from Ryan Salt. Steve is this purple arc. And today we have an amazing speaker, Neil Seller, who is an auroral photographer that was involved in the beginning of the discovery of Steve, and he's going to tell us a little bit of that story. From the beginning, we knew very little. So this first paper by Liz McDonald, Eric Donovan, Toshi Nishimura et al. Showed that Steve was associated with this very fast and narrow subauroral ion drift. And this is for one event. So today, Bill Archer is going to show us more events in which Steve is associated with SAIDs. I hope that Carlos Martinez will challenge a little bit of this, because Carlos will talk about the relationship between the narrow Steve arcs and the wider SAR arcs. And then Phil will tell us some contributions of Millstone Hill to Steve. And then Gareth will follow with ionospheric radar measurements of Steve. In general, also at the beginning, we had one study showing that Steve was not related to particle precipitation. So it wasn't formed like we know aurora forms. So hopefully Megan will tell us some of the characteristics that Steve has in the spectrographic measurements of Steve. And then Brian will tell us how the photochemical model can reproduce Steve. And then Toshi will also talk about magnetospheric drivers of Steve and probably a little bit of the picket fence. Closer to the end, Josh Semeter will tell us more about this picket fence structure that is usually observed. It's a secondary structure that is usually observed together with Steve. And then last but not least, we have Liz McDonald telling us about historic citizen scientist observations of Steve. So please submit your questions via chat in Zoom or using the YouTube chat too, and we will be asking all these questions at the end of each talk. So I'll stop sharing my screen and I'll ask Neil if he can share his screen right now. So Neil is, yes.
No, go ahead.
I just want to introduce you. So Neil is a member of the Alberta Aurora Chaser, and he's a very talented auroral photographer. So please, it's all yours.
Hi, everyone. Welcome to Cedar 2020, and thanks so much to Bea and the crew for inviting me to open today's talks. I hope my Steve chat puts smiles on your faces and gives a little bit of the background to the struggle of chasing all those crazy night lights. As you probably read, I am Neil Zeller, a professional corporate photographer out of Calgary, Alberta, Canada. I also host photography tours all over Western Canada, including the far north in the Yukon. I'm gonna fire up my screen here and share. Everybody see that? It's not a spelling error. It does say photon arc or whatever. Okay, what about my Steve? On August 28th, 2015, I spotted what I thought was a contrail in the sky over Lake Windermere, British Columbia. I think this is how it goes for anyone who sees a Steve for the first time. You see the streak, but normally you wouldn't pay attention to it, but it just lingers there. You point your camera at it and your life is never the same again. I saw that thing that night and I thought it was pretty cool. I'd seen a few photos of it in the past, but I couldn't remember what people were calling it, so I called it Bob. Kidding. Now this next moment that night will tell you how not scientist I am. I'm just a photographer, and probably reveal myself as a science fiction fan when I tell you that I couldn't remember what I'd heard this thing called and Googled photon arc. Google didn't answer me when I Googled photon arc on my phone that night, but I finally figured out by searching other photographers that I knew had photographed it, that it was a proton arc, and that I posted and said, hey, a proton arc on Twitter and Facebook to a smattering of oohs and ahs. Fast forward half a year to January 2016 in the Kilkenny Bar in Calgary. Dr. Liz McDonald was a guest at the U of C, the University of Calgary. And to all of us Aurora chasers, she was the face of Aurorasaurus and is a superhero to us. So I went to the bar to meet her. Imagine a bunch of Aurora photography nerds and a few space scientists sitting in this bar chatting all things Aurora and drinking craft beer. One nerd, me, says to one scientist, Dr. Eric Donovan of the U of C, over a beer and lively conversation, I've seen a proton arc. He says, no, you haven't. I say, yes, I have. He says, no, you haven't. This is actually how it went. I say, yes, I have, and I have a photo of it, doctor. He says, call me Eric. He says, let's see, and mumbles something under his breath like, no, you haven't. A proton arc isn't in the visible spectrum. What? I say, nothing, he says. So I showed him my proton arc. He called over Dr. Liz and Chris Ratzlaff of the Alberta Aurora Chasers, and after some back and forth and seeing more photos from me and others of this proton arc, he says, I don't know what this is, but it's not a proton arc. So please, 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 whatever you do, stop calling it a proton arc. Then we played bubble hockey. For people who don't know, I'm trying to change. That's the image, by the way. That's the picture that I shot on that August 2015 that I thought was a contrail. So, and that's the one I showed Dr. McDonald and Dr. Donovan. This is bubble hockey, by the way. So Dr. Liz and Dr. Eric and myself and Chris played bubble hockey against each other. I think, did Dr. Liz and I, did we win? I'm not sure, it doesn't matter. I've been very lucky to have photographed Steve many times since 2015. I've seen and photographed Steve in Saskatchewan, British Columbia, Alberta, and quite surprisingly, due to its northern latitude, the Yukon. This is not Steve, we'll get there. Now, whenever I'm photographing the northern lights, which are usually to the north of me in my Alberta location, I'm always checking up and behind me for Steve. It always helps to find Steve when you're actually looking for Steve. People ask me all the time, what is the best time of day to see the northern lights? I reply somewhat sarcastically at precisely dark o'clock. Okay, very sarcastically. So you'd think summertime wouldn't be the best for catching a Steve in my camera due to the lack of dark at my normal summertime locations with only 3 hours of astro dark at this time of the year. But in my experience, Steve is easier to catch in the summer. I am outside at more at night in the summer because why? It's not minus 40. The best Steves I've ever caught have been during our summer camping trips. I do give myself the best opportunity to capture the northern lights and by default, Steve, as we look for very dark places in the world to camp. Cypress Hills, southern Saskatchewan, and middle Alberta are favorite locations away from the glare of city lights. I've been chasing photography of the northern lights and now Steve since 2012. Notice it's not called finding aurora, especially at my latitude. Even 300 kilometers up the highway has a significantly better finding possibility. Once we arrive out in the middle of nowhere and the aurora is out, this is the easiest part of chasing. Once you're there, it's gravy. Even a clear non-aurora night of photography is good once you are out there. It's very zen to sit in the middle of nowhere and stare at the night sky. The hardest part is deciding to leave the house. We have a funny way in Alberta with the Alberta Chasers of ultimately determining if we should head out into the deep dark night, and it's marked by telling everyone, pants on. That means just what you think it means, that you're putting pants on and heading out into the dark night. But to get to pants on, it's quite the journey. The things you think about include, is it cloudy, raining, or snowy? Side note, I sleep very, very well when it's raining here. When it's raining here, I'm fully pants off. We all have multiple weather apps and we tend to use the ones that is most favorable to our quest in that moment. We look at the space weather stats. We look at all the stats all the time, every day, every hour. All of us who chase the northern lights are constantly looking at the weather stats and what the sun is doing. One thing to think about is public knowledge of a big aurora event. If the major news networks report a huge aurora event, then take your pants off. There is never a good aurora night when the weatherman says it's going to be great. And to be honest, around here, our local weather people look to us, the aurora chasers, to see if they should report. It's a bit of a circle right now. We think about, when was your last glass of wine? Aurora has caused many folks to not have an after work glass of wine or beer because what if it's a pants on night? It would so suck if you missed a major event because you were tipsy and couldn't drive anywhere. FOMO. So does everybody know what FOMO means? I think in this world you do. It's the fear of missing out. Chris Ratzlaff, our fearless leader at Alberta Aurora Chasers, is infamous for saying he doesn't think the aurora will be out tonight. Then the next morning waking up to thousands of photos of a banner night of the lights. I know for a fact today that there are chasers who still have broken hearts for missing the KP8 event that happened on May 27th, 28th in 2017. FOMO creates a kind of PTSD that can only be cured by finally being out under a major aurora event. Over time, FOMO diminishes as you capture big events. Most small events these days are pants off for me. I'd rather sleep. The other thing that people think about is work tomorrow. Aurora lag is a thing like jet lag. It'll flip your days over and hurt your chances of being a productive human being for the next few days. If there's a multi-day event, I know people who have simply called in sick or taken vacation days to recover. It's not just the shooting time out in the middle of the night, it's the carnal need to edit these photos as soon as we get home. It could be 4 o'clock in the morning and we're getting home and we need to edit these photos. We need to get into those cards and see what we actually captured. Posting these online and watching the reactions are as much the adrenaline rush as capturing the photos. I have another technique for capturing aurora that ups my chances of finding aurora. It's when we are camping or staying somewhere dark and safe. I call it set it and forget it. This means I put a clean memory card, a full battery in the camera, set the camera up to shoot over and over again automatically, then crawl into my camper bed. It's a better technique for star trail photography, but on many occasions I've woken up to the card full of amazing aurora. creates another type of FOMO, like why didn't I stay up to see this? But it's not as painful because you have the photo. The only real advice I give to people who are on a paid tour with me is your satisfaction of chasing the Northern Lights is exponentially increased by capturing them with a camera and not just by eye. There have been days where the Northern Lights would astound you, but very few of those happen in southern Alberta. But the technical ability to gather more light than your eye can capture, the camera sees more light and color and makes chasing so much more rewarding. That said, I'm going to flip through some of my favorite Steve photos, and I even have some time-lapse video to share if my technology works. So in Alberta, my home, I tend to be out more because it's right here. I leave Calgary. It could be 10 o'clock at night. It could be 2 o'clock in the morning. In the winter, we obviously have more dark, and all of us Aurora chasers have these giant abominable snowman outfits that we wear when we go out. So in my Alberta home, I photographed Steve all over the province, and it's been wonderful. Starland County, if you thought of anywhere to go to see the night sky anywhere in the world, it's going to be Starland County, correct? It's a wonderful place, extremely dark, away from away from city lights, not that far from Calgary, maybe a 2-hour drive, and we camp out there all the time. This image here with the picket fences was a night where I got to share it with my whole family. My parents, sister, wife, and son were out, and they came. It showed up at 11 o'clock at night, which in the summertime is, we still got a couple of hours of near light up here. But it came out and was so strong and beautiful. That night was really something. Same night, a little later on, straight up into the Steve that night with the picket fences. And this is an interesting Steve. There's a blob aura. Do you guys have, who's investigating blob aura these days? I hope somebody is, because it's a real thing. This by eye, people wouldn't notice it. Like the regular layman wouldn't see this and find it, because we're looking for Steve. We find it and shoot it. I hope people can see the video moving and the flow. I love how Steve follows the stars, not the earth. That one night in Saskatchewan, I think some of you in this room today are that you may be talking or studying this night in Saskatchewan. This was the first I saw of Steve that night. I'd gone down to the lakeside to photograph an Aurora event, and then went back to the camper, and I was sitting there watching the sky and the fire, and I noticed just a hint of that streak up there. And it was one of the most banner nights I have ever seen for Steve. It was mind blowing. An hour and a half of some of the brightest, most incredible Steve you'll ever see, with a glass clear lake for reflecting in. Had everything that night. Even just picket fences. Little bump of the camera. I kick the tripod in the dark every once in a while, and my time lapse shifts a little bit. It hurts my feelings, but it works out. Last year in the Yukon, in September, we were up there. I take tours, and we were at our cabins north of Whitehorse, and everybody had gone to bed, and I was still out, as I do. And I noticed Steve in the Yukon. I didn't realize it was a northern phenomenon that you could see that far north. I'd seen a couple of photos and wasn't sure if they were real, but I am a true believer now. This is our cabin in that night with Steve over us. It was really something. There's some interesting changes that I noticed to Steve in this one, and that even the picket fences look like lines, I believe, because we're not looking at them from the side, we're looking from underneath. Yeah, it was a night. And another thing that I noticed too is the Steve, if you can see in the middle, the purple, the Aurora line had moved beyond Steve from that latitude. Not sure what that means anything, because I'm not a scientist. First time I had ever observed it. The Aurora is typically far north from it, but I think it might have something to do with altitude. I'm not sure. Yeah, it was a night and a half. I found where Steve comes from, though, that tree. This is just 2 nights that night. Watch how the Aurora encroaches the Steve. it was warm then, so I didn't have to typically in the winter when I'm shooting northern lights, I make a little nest in the snow and I sit in it so I can see up easier as opposed to craning my neck. Top of the world in the Yukon, you see a lot of satellites. I don't know if you can see them moving around back there, but okay, so that's my initial talk about the beauty and the chasing of Steve. Thank you again. Who wants to talk about Blabora? But that's a whole nother thing. So I'll stop share. Thank you everyone for paying attention to my beginning beautiful part of this Steve presentation. Thank you.
Thank you so much, Neil, for an amazing presentations. Do we have any questions from the audience?
So Bea had one there, Neil, essentially where you had Steve at the zenith, where you were almost looking under, you were almost under it, was north to the top. She was wondering about the compass orientation.
Yes, north was to the top. In most of my Steve videos, it feels like that's the right way for me. Whenever I'm shooting, I end up with my back to north with the camera straight up. So yes.
I was asking that because you can see to the top of Steve, you can see diffuse aurora, and then towards the bottom of the camera, you don't see anything.
Right.
Correct.
That is
yes.
really interesting.
Yeah, there's a definite marker that I've noticed when Steve is out that you have that kind of hazy green until Steve, and then just clear duck sky from that moment, from that spot.
And Liz mentions, you know, she'd like a word or two more about the blob aurora, a stable co-rotating blob at subauroral latitudes, and she's entirely right. That's perfectly on topic.
Good. Do you want me to talk about that?
I think she's wondering
Asking.
about, yeah, just maybe a little definition for people who hadn't looked at it before.
Yeah, so blob aurora I've seen 3 or 4 times in my years of shooting Northern Lights now, and it's a stable, located aurora looking green blob that sits and pulses in place, and it's always on the same line that Steve shows up on, that sort of east-west, away from the regular Northern Lights location. So a number of us have seen it. Chris has seen it. John Anderson in Alberta here have seen this blob. I've got a little video of it that I didn't put in this because I didn't think blob was going to be a topic. Yeah, it's a very, very stable lump of Northern Lights. Is kind of my scientific interpretation of that.
Okay. There's a couple of other technical questions. So Neil, one person asks what the time exposure is per exposure, and then what kind of image processing do you do after the fact? Is that true color or enhanced color, or what are we seeing?
What's true color in the middle of the night? To be honest, there's a lot of interpretations of what it comes out as. Just if you look at it by eye, in most locations, there's it looks gray, right? It looks like you can tell it's Northern Lights, you can tell it's moving, but a lot of it is it's more of a whitish gray light that's, you know, not typically in the night sky. So you see it when you photograph it. Your camera's abilities to capture more light and color come true, and you get to see what the colors are. We have an understanding because we've seen them very, very strong in our latitudes and up north, green and cranberry and red and purple and white, all these different colors. So I think as an artist trying to interpret the colors, I'm not trying to go overboard to what the colors, I'm not trying to under show them, but it's always a little different by eye. There's been a few times in my experience where the auroras can't be captured because they are too bright, too colorful, and too fast. And that's usually up north, north of 60 latitude. And those are the ones that bring tears to your eyes, that just, they blow your mind. So sure. For processing, as little as possible to sort of explain what it felt like and what I saw through the camera's eye.
Hey, I don't know how much, there are more questions, but I don't know how we're doing with time.
Maybe we can try to talk about those at the end. If we have time, we can come back and ask.
We'll aggregate. Yep.
So our next speaker is Bill Archer. He's from the University of Saskatchewan, and he will tell us more about Steve, the subauroral iron drift phenomena. Bill, can you show your screen? you.
There we go. Now I'm unmuted as well.
There you go.
You have 10 minutes.
Wonderful. Wonderful. So I'm actually gonna keep it pretty short here, I think, because it was quite interesting when I was making this presentation, and I typically try to provide a little bit of a background slide for general knowledge for people so that they have the appropriate context for what it is that I'm going to talk about. But when I read the list of speakers, you have a talk on every point that I would mention, and so I'm really excited to listen to them all speak. So that being said, that means I will focus on actually how I was first introduced to Steve, and so you showed this one of these two figures from the McDonald et al. 2018 paper, and so some researchers in Calgary had recently found this event and they were pretty sure they were looking at a Steve event. They hadn't yet confirmed it with sort of rural photographers, but they were also curious, hey, were there any satellites flying through this? And I was working down the hall, and they knew I worked with the swarm satellites, so they said, hey, was swarm in the area, and was everything turned on? And that's an ominous question for anybody who works with satellites. But in this particular instance, we got this beautiful data that we see on the right here, where as Bea said before, we found co-located with the optical signature of Steve, we saw a narrow flow channel on the ballpark of 5 kilometers per second. We were at the poleward edge of the mid-latitude density trough, a very sharp trough, with associated in this case with a sharp electron temperature spike, and we were in a region of sort of weak downward current, and so downward field line current, and so all of this is typical of a subauroral ion drift event. Although 5 kilometers per second made us wonder a little bit, because that's pretty fast. And so I think I'm just going to take a second, because I think the notion that Steve is associated with a subauroral ion drift, that's a very simple statement. That's and that's more or less all I'm talking about today. But I think it's an important one, because if it's true, if that's a correlation that we can just run with, that has a lot of impacts on how we proceed forward with analyzing this event. And so the follow-up study that we looked to accomplish was essentially just trying to be as confident as we could possibly be. Is Steve associated with subauroral ion drifts? And so Bea actually had found 30 some events in the all sky imager data. And 8 of them had swarm satellites passing near or through the actual event. Sort of spoiler, we do find that these events are consistently associated with the latitude density trough, with a strong electron temperature spike, weak upward field line current, and a narrow flow channel. And so to show this as a graph, there's an awful lot of information here, but so each horizontal row is a different event. And so, you've got the electron temperature and plasma density on the left in red and blue respectively. And then you have the field line current and the cross-track ion velocity on the right. And so even if, especially if you look at the sort of plasma density and electron temperature, you see, sort of a very consistent ionospheric picture these events. And there were unfortunately only 4 of them actually had plasma flows associated with them. And this big arrow on the screen is pointing to the event that's the McDonald et al. 2018 paper was written about. But all of this shows a pretty consistent picture. But this still asks the question, okay, we have some flow velocities here, and we can say they're big, but how big are they compared to a quote unquote regular subauroral ion drift event? And so to try to quantify that, we identified as many events as we could in swarm data. So we were using the same instrument set, and we found 122 events within a year's worth of data. And then we can compare the sort of histograms of the plasma parameters associated with those events to these events that we saw, alongside Steve. And so we've got these 4 histograms now, where you've got, from upper left to lower right, we have peak ion velocity, field line current, sort of integrated over some region surrounding the Steve event. And then you have peak electron temperature in the bottom left and minimum plasma density in the bottom right. And so, what we found is essentially that, consistently these flows, especially if we focus on the events in which the satellite passed directly through Steve rather than, sort of beside it, as it were, or perhaps outside the field of view of the camera, consistently, we've got sort of, 4 or 5 or even higher, in all of the events we have very fast ion velocities. The field line currents, it's not obvious whether these are extreme in any way relative to a normal event. It's sort of hard to say from the data we have. But the peak electron temperature is quite large. This one in the graph in the bottom left-hand corner, this B event is quite a bit of an outlier. And if you ignore the top data point and just say, let's take the second highest temperature recorded, because this is only a single point is that high, it brings it in line with the sort of EHG events, sort of around 8 or 9,000 Kelvin. Anyway, and also the plasma density, it's extremely low relative to the typical events as seen by swarm. So, I mean, ultimately, the take home from this is, I think we, of course, would like to have more events to be more confident in this, but the very important point was that we didn't find any counter examples. So we didn't find any Steve events where we had measurements and we didn't see the signature of a subauroral ion drift event. That's the, if somebody shows me a very, great set of data where there's a Steve and there's no subauroral ion drift, then we have to, and I think, what's the fun thing, the exciting thing about these results from my perspective is they really redirect the conversation. It's not what is this anymore. It's, you can approach it as, well, why would a subauroral ion drift have an optical signature? And I think they, played a significant role in constraining some of the initial model on Steve, which somebody will speak about in roughly an hour's time. And so that's all I have for you guys. I'd love to hear any questions you have.
Okay, so we did have one question. Did you look for the DMSP data associated with these when you were doing the, identification of the swarm measurements? Right.
So I did not. And part of, so there's the primary reason for that is ultimately that I'm a lot more familiar with swarm data set than with DMSP. I did look at events and try to find them. One of the nice things about the swarm satellite event is that, or the swarm satellite is just the MLT where it flies. That often, since it's dawn dusk, the DMSP satellites they will catch some Steve events, but it is a lot less common simply because Steve is typically found right around midnight.
Right, and so there was also a comment, the correlation between density and current and flow velocity, because for an SAID, there's typically an anti-correlation, low density, high velocities, not necessarily requiring large currents. So I don't know if you had any comments about that.
Yeah, no, that's absolutely, the stronger the event, the lower the density, the higher the electron temperature, the higher the flows. So now for the specific events that, the small number of events I have here, specifically associated with Steve, you can't necessarily see that correlation, but yeah, if you look at all 122 subauroral ion drift events, that's certainly present. Yeah. And so, that's typically, the takeaway from me, when I look at these events, is that Steve is associated with a extreme event, and I'm not going to specify, it's in every way, because all the plasma parameters that tend to go along with the subauroral ion drift, they tend to, they relate to one another, so they tend to sort of all go together.
Okay. Bea, how are we doing on time?
Maybe we can ask our next speaker, that is Carlos Martinez, to start sharing the screen, and maybe we can take one more question.
Okay, so one of our conveners, Barat, asks, are there any comments on the upward field aligned currents associated with Steve? Is that somehow related to the substorm current wedge phenomena? Maybe that's not a short question.
Yeah, that is not a short question. Yeah, I think if we wanted to approach,
I can make a comment about it. So
okay.
Actually, that upward field aligned current was what gave us the idea of it not being particle precipitation, because the current was in the opposite direction, right? So we don't know exactly what is producing that current system yet. And I think, remember, this is in the subauroral region. So I think we are a little bit too equatorward for the substorm current wedge to be observed there. We are not within the auroral oval. So that's my comment.
Okay.
Let me maybe comment. Actually, the current, field-aligned currents associated with whatever, SAD or SAPs, if you want, they are pretty strong sometimes. They exceed a few microns per meter squared, which is comparable to some auroral events. It's not every time, but anyway. And it has to do with, of course, region 2 current, which can be, as we know, split it into small scale structures. And this is current, electromagnetic, actually, structures. So there is no wonder that, you see the currents and you see structures in a globe.
Yeah, to keep things flowing, feel free, folks, to type in the chat and discuss that while we continue. I think that would be good, because there's a couple of other comments in there.
Okay, can you hear me?
Yes.
Yeah. Okay, so this is very nice. I enjoyed the first two presentations. I'm pretty sure I will enjoy the rest of the presentations. And Bea put the title of my talk, Steve's versus SAR-arcs. And I decided that we have to talk about Steve's and SAR-arcs. Just a quick definition of SAR-arcs is an subauroral feature that we observe in using optical instruments, typically monochromatic, only in the 6300 angstroms lines. They share several of the characteristics of Steve's. So if you make a table of similar characteristics and different characteristics, you can see that there is almost 50% of things that are similar and another 50% things are not similar. Basically, we can say that main difference is Steve's you can see in all wavelengths. Steve's tends to be very short-lived, while SAR-arcs tend to last for hours and even days when you observe in consecutive days. SAR-arcs have been seen to span the entire globe. So these are large scale. And a common characteristic is that SAR-arcs tend to be associated with these enhanced temperatures observed by satellites, as well as those decreased ion densities that are observed simultaneously. And the difference is that for SAR-arcs, you don't need these extreme conditions that Bill was just mentioning. So today I will be presenting two cases that have different nature. So you think you will finish one case and that's a story, but no, then I will come with another case that will tell you a story different. So And this is in addition to a case that I presented last year, in which I was arguing that the definition of one of the Subauroral structures as a STIB, in fact, was not correct, and I was saying that was a SAR arc, but that's in the past. So let's go next figure. If I can move. There you go. So let's start with this beautiful picture from Alberta, Canada, one of the citizen scientist photographs. In this event, there were individual frames taken on this night on 28 September 2017 that Alan made in an all-sky panorama view. Very nice, because this is a perfect way to use to combine with our all-sky imaging data. That for this particular event is not show a marginal event in the East Coast. For this event, the main comparison comes from one of the sites from the Mango SRI network. And Asti was very nice and shared the data, so I will be discussing those data. And the point is here, you see very nice Steve with Aurora to the north. And this is another view, a rectangular view with a nice moon here to the south and the Milky Way. So on this night, here on the bottom, you see the network of Mango all-sky imagers in white, and I added 3 additional fields of view. Here to the east of North America is the Milson Hill view imager. The top circle here represents the field of view of Lucky Lake. That's a site from the Rigo network that's been used a lot for STIB studies. And this is a field of view of the Aurora picture that was shown in the previous slide. The point here is that during this night, a SAR arc, as I say, was visible for many hours, spanning the entire North American longitude sector. These are different raw images from the Mango network, showing a very weak arc here around 8 UT, and from Madison, Kansas. More to the east, Eastern Iowa Observatory, another SAR arc is at 550 UT, you see it there. And here, all the way to the east of North America, we have Milson Hill, where you see the Aurora to the top, and an arc that is not very bright. And this is something that we have observed many times. SAR arcs tend to be observed not always as a nice uniform arc, but as in this case, like a voided area here with no brightness, but to the east and to the east and west, you can see there is some brightness. And this is happening at 4 UT. Evidence that this is not likely a STIB is because we look at the other wavelengths that we can measure in this system, and there were no additional observations matching the location of this arc. So taking the Bridger data, in particular, these are raw images. I don't know if you can see with detail here, but we are doing here, we're taking 6 different frames starting at 435 UT. This red square represents a very weak arc that we say represents a SAR arc. To the north, you see the Aurora. And starting at 450, you start seeing like an additional arc that is coming from the north. It's like detaching from the bright Aurora that you see. You can notice that it's very asymmetric in the sense that it's brighter here to the west. By 455, basically this is indicated by this pink purplish square. Basically, this is the only arc that is observed, while here was the location of the very weak arc is hardly observable. This is 455. Later on, by 520, that very bright arc is gone, and you start seeing again this weak arc shown here, that as time progresses, you start seeing it's becoming very, very bright. In the bottom is like, these are different cuts that were taken through these points indicated on the top images, just to show that here, this is a very weak signature of the SAR arc. And by 450 and 455, the pink arrow shows the location of the STIB that we are saying that is observing this imager in addition to the SAR arc that was existing before. Now, this is a busy plot here to the left. Is we took the all-sky image from the Aurora photographer, and look at the field stars, and we're able to unwarp to a given altitude, in this case 250. And we did the same thing at the bottom with Bridger. Here, this bright feature here is the moon, as you can see here too. And just to facilitate the comparison, we added dots or small dash lines into the arc, the bright arc that was observed at Bridger. We did the same thing at 400 kilometers, and you can see more clearly here. This another trace was done at the weaker arc. Hardly you can see it here, but the point is that with these images, we went every, I think, 25 kilometers, and we went from 200 kilometers all the way to 400 kilometers, trying to see where these structures will match. And here to the right, you have a very broad summary showing that starting at 200 kilometers, we superimpose the two images, and you can see the trace lines are not following the image observed by in Alberta at 200 kilometers. When you get to 275 kilometers, the matching is much better. When you get to 300 kilometers, the matching is still good. And then I jump here to 325, and you can see how now the offset starts to be in the different direction when you compare it to the offset happening at 200 kilometers. So here I'm doing just this just to indicate that the height of this phenomenon that we call Steve is between 275 kilometers and 300 kilometers. There were not satellite passes going at this particular time in the Northern Hemisphere, but there was a DMSP pass in the conjugate location. And this is an example. We took the image from Bridger, we mapped it to the Southern Hemisphere. It's not very clear, so we added here just trace lines just to indicate this is the Steve, and this is a very weak arc. And we took the electron density, or ion density, electron temperature, and horizontal velocity. And interestingly, we think that there are two features that can be associated with the optical structure we see. The red dot represents the location of the conjugate SAR arc, and we can see it's located in a region of low density with relatively high electron temperature. I don't know about this arc of ion velocity, seems to be nothing, but more intriguing is this very large jump in density here and in temperature, as well as in velocity. If you see this, this could be a typical SAID, almost 5,000 meters per second, very large electron temperature. But when you try to match the location of that bright feature associated with Steve in this map, we have the location here. So we need to work this. It has involved mapping from one region to another region, the DMSP altitude to some altitude in Southern Hemisphere. So we need to work, see if this indicator could go there. But I think this is a clear evidence of the signature from the satellite of the two optical structures we see, like different stuff. Now we go to another event. This is happening in the Southern Hemisphere. This is another beautiful picture. There's a movie showing how in New Zealand, starting around 920, we see a very bright arc that I say is a SAR arc, and how it evolves to the way that in less than 1 hour, that very bright red, wide arc becomes a very thin, kind of whitish, purplish arc that we associate with the Steve. Not shown here, but a few minutes later, this arc is almost disappearing, and you have peak and faces going through the field of view here. So, working with Toshi, we took this image from the auroral photographer, and we did similar analysis, and we unwarped this. These are more work needs to be done because of the lack of linearity on this projection. But the point is that you can see this bright arc at 9:24. That's the time that we see this arc is being observed, that we attribute as a SAR arc. It's to the south of New Zealand. Boston University has one imager at Mount John, and that imager showed there was a bright arc, obscured by clouds here, as you can see, but there are areas where you can clearly see that there is air glow. These are calibrated images, so we can get a real value of the brightness. And for this particular event, where you can see that the location is matches pretty well the observations from the ground, the aurora photographer. In this case, the bright air glow associated with this arc was around 5 kilorayleigh. So this is very unusual, and this explains why you can see so easily with from the ground. Unfortunately, the last data in this with the image was at 9:38, because after that it got all cloudy, so we couldn't follow the evolution to a bright structure associated with Steve and what would have looked like. But fortunately, we have very nice pass from swarm. Let's start from in the bottom. This is a pass going from 936 to 940. This is a field of view of the imager Mount John. The swarm is moving northward. And you can see here very clearly the location of the, in this case, the arc structure with an increase in temperature and a decrease in electron density, and a very nice enhanced westward flow. Now, the satellite is moving northward, and by 10:03 is reaching the northern hemisphere close to the geomagnetic conjugate location of Mount John Observatory. And at this point, basically at the same geometric latitude, conjugate latitude, we see similar features, but in this case, these features seem to be more pronounced, with the temperature reaching a couple of points, almost 12,000. But if you ignore those 2 points, you come down, you're still very high, 10,000 degrees Kelvin. And the flow seems to be much larger, almost reaching 10,000 meters per second, or if you don't trust these values, get down to 8 kilometers per second, still very large. So we are thinking that what is happening here is in the southern hemisphere, the satellite is sampling SAR arc characteristics. And when it goes to the northern hemisphere, that SAR arc was converting to a Steve, where the in situ measurement showed that there were some more extreme conditions. So in this case, this is the evolution from a SAR arc into a Steve, not two things coexisting simultaneously. So finishing up, yes, this is a summary. The first case was a weak SAR arc observed in the entire North American sector, lasting all night long. By combining citizen science images and scientific images, we can show that Steve was occurring around 275, 300 kilometers, lasted only 20 minutes. And this is an important result that I'm pretty sure Brian later will address, because the mechanism proposed for brightness, I think they cannot account for a structure occurring so high in altitude. Another interesting thing is with the red line imager, the Steve wasn't uniform. It was brighter to the west and was not well defined to the east. I don't know if there's something to take into account when you compare with the ground-based data. And finally, the second event in which we saw a SAR arc observed by both systems, the calibrated images showed that the SAR arc was very bright, around 4 or 5 kilorays. Remember, typical values are around 400 rays, 500 rays at most. We think that we observed that the SAR arc evolves into a Steve, and we think that swarm data show conjugate SAPs or SAD signatures, indicating that when it's moving in the northern hemisphere, before was sampling a SAR arc or SAPs conditions, if you want, or weak SAD conditions, but when it gets into the northern hemisphere, is already measuring these extreme conditions and can be associated with Steves. And with this, I stop. Thank you.
Carlos, we can quickly ask you one question, pass on one question before Phil sets up his slides.
Yep.
Can you provide some more information about the conjugate site in the first event that you showed? I think this question is from Jessica.
Yes, so basically we took the coordinates of the Bridger site, and we follow using IGRF, a geometric field model, into the southern hemisphere. And from there, we, at a given altitude, we took DMSP data and we mapped the measurement from the DMSP data, 875 kilometers, into the altitude that which we mapped the image. And that is something that allows us to make a comparison. There's an uncertainty in these altitudes because we don't know exactly if it's 300 kilometers or 270 or something more. But we are confident that the 270, 300 kilometers is a right range. So we need to still investigate why the DMSP data don't match exactly the optical structures.
We can quickly move on to Phil. And there's a few questions in the chat window. Maybe you can answer them there.
Okay. Thank you.
Phil, microphone.
There. Can everybody hear me?
Now, yes.
Thank you, Evgeny. Okay, so my goal here is really to just, I'll provide these as PDF and there's some paper references. My point here is really just to save some time and remind people that there are a few things we do know about the subaraural ionosphere, and some of which, now that people are beginning to zero in on the optical emission and maybe the electrodynamic conditions that drive it, we should consider as either preconditioning or climatological conditions that some of these extreme structures may show up in. For any students, by the way, the first thing here, I've got a few definitions of people who have been using SAIDs and SAPs, and there's a couple of different references in here. My point is that this larger sort of SAPS envelope that you see in the that I'm pointing at right here in the lower left-hand corner can sometimes develop or be co-located with these very sharp SAIDs, some of which have large enough velocities and high enough temperatures that they're causing the structures that we're talking about today. So between Phil Anderson's work with DMSP and Russell Landry, and then the work that Bharat has done with Superdarn and the work we've done for Millstone Hill, there's a lot of climatology on the general SAPS envelope that people can rely on. And in particular, I want to mention that in addition to, for Millstone Hill in particular, in addition to the work that John Foster did almost 2 solar cycles ago, and then I updated a little bit a few years later, my colleague Urcha Ah has actually added 20 more years to our Millstone Hill radar database on SAPS. So now we have 1,500 event profiles. He's about to release a paper where he's actually done a superposed epoch analysis of all of this from MLT, seasonal, KP, F10.7, and IMF. So the point is that we have an updated climatology that can be combined with the recent stuff that Bharat just did a couple of years ago. And so there are some models of the general SAPS environment which one can rely on. And so those of you who haven't looked at that, I encourage you to look at that literature and keep it in mind when you're thinking about perhaps the conditions that are where these extreme events are occurring. I will also mention my colleague Shenrong Zhang's work on the fact that these large intense flows, in this case SAPS, so a broader flow than the narrow SAID we've been discussing today, if they're there for long enough, and sometimes SAPS can spin up and be there for long enough to spin up the neutral atmosphere and create very large neutral winds, which then will cause frictional heating. So those are all not necessarily normal conditions in the subauroral ionosphere. So that's another thing to remember when you're considering the background conditions that something like a Steve might be occurring in, and also thinking about the optical pathways that lead to those enhanced emissions. And people who are far more capable than I am are going to talk about that a little bit later. Finally, I want to mention a couple of other brief things. This is a really dynamic region, especially with the conductivity and fairly intense electric fields. From Millstone Hill, we saw that the overall SAPS envelope can have these embedded small scale, sometimes as small as 10 kilometers or smaller, instabilities with a short temporal lifetime of 1 minute. And the point is that all of that fine scale structure can occur within that broader SAPS envelope. And again, when one is considering Steve, it would be useful to look at whether one can detect that that fine scale structuring is emerging out of a broader SAPS envelope, again, within the region 2 current system that has been discussed quite a bit, I see in the chat. Finally, I want to just mention a couple of other things that are coming out in the literature now. Back in 2004, Anatoly Streltsov and John Foster were actually looking at an interchange feedback and interchange instabilities between the ionosphere and the magnetosphere that were leading to highly structured field-aligned currents. I noticed that Evgeny Mishin and Anatoly published a paper last year where they were talking about similar sorts of structures that, again, could be associated with Steve conditions. And so it really is truly an MI coupling sort of feature. And my point is that there's some good theory to lean on. And the left-hand side of the page also shows you that there are also, highly structured oscillations or wave structures. SAPS WS has been labeled again in this region, and it would be interesting to see how Steve is emerging from these conditions. And finally, just want to leave a reference to the paper, the fact that there is this injection and plasmoid theory that helps explain why SAPS occurs and SAID occurs so rapidly after substorm onsets, really too fast for a lot of gradient curvature drift of the normal things at ring current energies. So timing, if we can ever get enough simultaneous measurements here to look at the timing and we have enough magnetospheric information, I think there's, again, a lot of knowledge here that could be poured into what we're doing with Steve. So again, it's my goal here is just to remind people there's a lot of good reading in the last decade or so in the literature that I think we should all kind of come up to speed on when we're trying to put the larger picture together. So I will stop there.
Any questions for I think?
I'll say something.
Hey, Larry, go ahead.
Good. You were just talking about the rapid flows, like 30 minutes after a substorm. And one thing that happens during the substorm expansion phase is a lot of streamers, which are flow bursts in the plasma sheet.
Mm-hmm.
And our leader, Bea, has written a very nice paper on the connection between those and rapid flow bursts in the SAPS region, which are said things. So the connection that you're looking for is almost certainly the expansion phase streamers, which are substorm current wedgelets. They actually form the substorm current wedge, and leading to these SEDs and Steves and SAR arcs and things like that.
So you made the excellent point that again, there's a lot we can know about that part, and I know it's a complicated picture, but this is kind of requires, it's a challenge. We have to sort of try to put all of these pieces together. I'm encouraged that we're getting to the point with Steve where we can do that, I think.
I think you'll find Bea's paper is a good guide for you.
I agree.
I have a comment also. It takes time actually to make a good, you hear me? Make
yes.
A good density trough even inside a strong electric field westward flow. Basically what you have after substorm during streamer interacting with the plasma sphere, you have very quickly electric field established, or westward flow if you want, near midnight. And then it penetrates into the ionosphere. It's about a few minutes time delay from what happened in the magnetosphere. But then when you have electric field established, you need time for plasma chemistry work on the deep density trough. It's usually about 5–10 minutes. So that's a characteristic time scale. You have substorm injection, you have electric field in the magnetosphere, in the plasma sphere, just equator of the earthward of the auroral boundary or plasma sheet boundary. And then another 10–15 minutes you need to create a deep trough, which characteristic signature. That's kind of time scale to find out.
Thanks, Evgeny. We might want to quickly move to Gareth, who's going to talk about Steve observations using super-down radars. And there's also a question by Rod Heelis in the chat. If Phil, if you can address that.
Yeah. Okay. So Rod made the Rod made the comment that said, you know, a large ion velocity should lead to a ring distribution function. So has anybody looked at the effect of those kinds of things on vibrational excitation of, like, I'm assuming, molecular nitrogen? Maybe it's something we can keep in mind as we go.
All right, should I start my show?
Yes.
Yes.
Have at it.
Okay, good. Everybody can hear me? Okay. Good afternoon, everybody. My name is Gareth Perry. I'm from the New Jersey Institute of Technology. I very much wish I could be in Santa Fe with all of you, enjoying a drink on the patio, but overlooking that square. But this is the way it is. So I'd like to thank the organizers for allowing me to speak a few minutes about Steve and about Superdarn echoes relating to a few Steve events. So I'd just also like to recognize my co-authors. So we've seen several Steve events with Superdarn radars, with HF radars. And these are confirmed Steve events, which we've seen with optical data. And I think you've seen a few of those cases already this afternoon. Bea sent me, or one day, I guess, when I walked past her office when we were both at Calgary, showed me some data of Superdarn during Steve events that she said, I want you to take a look at this and tell me what's going on. And so I agreed to, and two events kind of really stuck out first for us to look at, that we wanted to look at, because they're both from the Christmas Valley East radar, and they both show kind of two different characteristics of Superdarn radar echoes during a Steve event. The first one is we see radar echoes happening before a Steve event. A Steve event happens, we see Steve in the optical data, and then the echoes suddenly disappear. That was the first event, which I'll show you in the next slide. And then there's another event where we see that same pattern, radar echoes that then disappear when Steve occurs, but then they reappeared, these echoes, and they formed a line of echoes along the optical emission of Steve and followed Steve along. And so these effects seem to be only seen in one radar. This is Christmas Valley East. And so as Neil Zeller, I guess, introduced me to the Alberta Auroral radar, Alberta Auroral chasers, expression of putting the pants on and getting to work. So that's what I did here for Bea, at Bea's request, I guess. So this is the first event. This is July 29, 2016. And here we have the North American continent. We see a lot of tilings here showing the Doppler shift, various Superdarn radars. What we see labeled is Christmas Valley West. This is CVW. And then we have Christmas Valley East. This is CVE. And up here we have Saskatoon. So we have two auroral imagers. And what you'll notice is Saskatoon echoes will change, but they'll always be there. But during the Steve event that'll come down from the north here, from just over Saskatoon, you'll start to see these Christmas Valley East echoes disappear in time. So I'll go ahead and try and play this. Hopefully everybody can see it. So what you'll see is the echoes are now disappearing here at Christmas Valley East, just before our Steve event appears. Meanwhile, Christmas Valley West, Saskatoon, it's going to loop here. All these radar echoes kind of seem to be unaffected by all this. So this was a nice event, very curious event. And so that was the first event that Bea showed me. And then she showed me another one from September 27, 2017, where we again have some of the same radars. We have Christmas Valley West, Christmas Valley East, and then we have some radars down in Kansas. For some reason, Saskatoon data wasn't here, and I'm trying to remember if that was because it wasn't available or for some other reason. But nevertheless, we still see a same effect in Christmas Valley East radar echoes. So I'm going to go ahead and play it. We see echoes disappear just before preceding the Steve event. The Steve event appears out of the north here, but then, as you'll see, the echoes reappear and begin to line up nicely with the optical emission of Steve and stay there and follow it along. And these are Doppler colored tilings, so you can actually start to pick up. It's not scaled properly. You don't have a scale here, but I do believe the blues are away from the radar and the reds are towards the radar, so you can start to make out some flows here. But the point is, we have what Bea kind of showed me and what she asked me to look at is that we had these two events observed by Superdarn showing kind of two distinct characteristics of how the echoes are acting in this dynamic event. So the question really that's motivating this work, and that kind of is motivating here, is that why do we see these specific Christmas Valley East echoes disappear during a certain event in the first place? Why are they disappearing? And we know it's not a radio absorption event. So we know from Bea's work that we don't have this really hard precipitation agitating the D region, which would then absorb the HF emissions. That's not happening here. So it has to be something else. We also know that it's not a matter of the radar operating conditions changing. We checked, and in both these cases, Christmas Valley East radar was transmitting in between 10.4 and 10.7 megahertz. So really, in general, to get radar echoes with superdarn, you need two things. You need, well, three things. You need the radar to be operating. You need irregularities to be present, and then you need sufficient propagation conditions to allow your HF transmissions to satisfy the aspect angle condition at the point of the irregularity. So you need those rays to refract such that they're at more or less close to a right angle with the local geomagnetic field. So to really kind of go after this question of why do we see these echoes disappear, we first started looking at that the propagation question and whether or not that this disappearance of echoes could be due to, the disappearance part could be due to the fact that we had a sudden change in the propagation conditions on the order of tens of minutes that changed so significantly that they made the echoes essentially disappear. So that's the hypothesis we started attacking. And just to kind of show another shot, this is a range time intensity plot from Christmas Valley East. We have slant range or group range, if you must, on the vertical axis. And just look at the top panel, that's echo power. And we see this is beam 7. And we see from about 4 o'clock to 5 o'clock, we have this band of echoes at about 1,500 kilometers. And then those echoes start to disappear just after about 5:15, 5:10 UT. And that's when the Steve event is happening. So the question is, why do these echoes disappear? And the hypothesis is that we have this deterioration of these HF propagation conditions, preventing the rays from meeting the aspect angle condition, assuming that there are irregularities present in the vicinity or in the area. So what we did to look at this is we took Ray Tracer, which is the FarLap ray tracing toolbox. It's in MATLAB. It's produced by Cedar out of Australia, and it's a very, very nice and very useful ray tracing tool. And what we did was we essentially just did some ray tracing simulations using FarLap of the Christmas Valley East radar, but kind of tweaking the IRI ionosphere to try and match what has, to try and kind of recreate this echo disappearance effect. And so FarLap both uses IRI and IGRF. Another input we used was Swarm, which was going through the area at the time. So we had Swarm A and Swarm C go through. And on the right here is just a plot of geographic latitude on the vertical axis and plasma density on the horizontal axis. And the red and black traces are the swarm radar plasma density measurements taken at about 450 kilometers altitude. And the purple or magenta lines are what IRI tells you what that plasma density should be. So you can see that there's quite a discrepancy in what IRI is telling you and what a spacecraft in the vicinity is telling you. And Swarm was going through about half an hour after the Steve event, so it's fairly timely. And you can see that the plasma density profile at this topside altitude of 450 kilometers is quite dynamic. I mean, that slope, that equator side slope of this Steve event or this SAID is quite dramatic. So what we did was we essentially took the swarm data and tried to incorporate it into IRI, or tried to make them match, and then run the ray tracer to see if we could reproduce this event. So on the left here is a vertical versus latitude profile of the IRI output at about 5 UT. The red trace is showing the Swarm A track. That's the altitude of Swarm A. And on the right is Swarm A incorporated into IRI. And so essentially what we did is we forced IRI to look like Swarm A's profile. And we kind of we naively, now this is, again, I use this term, naively mapped that structuring down into the bottom side F region. We weighted a bit such that we wouldn't get these obscene gradients in the ionosphere. So we applied like a Gaussian weight here and fiddled with this. we imposed this vertically, and then we did this in time just to try and see if we could recreate this disappearance of echoes using IRI as a start, a fade into what Swarm was seeing, and then a fade back to what IRI was seeing, just to see if the propagation conditions actually did fit or did recreate this echo disappearance. So we run the ray tracer, and what we do is we assume that there's irregularities everywhere, and we just look for where the rays meet the aspect angle conditions. So that's where the wave normal is at right angles with local B, and wherever that occurs, we would just say there's an echo occurring. So on the left is a range time-esque output from this ray trace model where you have group range along the vertical axis, and then your time and UT for these July 29 event 2016 along the horizontal axis. And you have all these plots that are color-coded by the altitude of where our echoes are. That's where the K dot B is equal to 0 or close to 0. And then on the right is when we faded in and out that swarm-constrained IRI ionosphere. And so what you see is right about the time where we have this Steve event, excuse me, my timer's going off. The Steve event occurs is that indeed we do see this group range kind of, the group range of these echoes increase and then completely disappear. So that means that your aspect angle condition is no longer being met. And it more or less is consistent with what we saw in the SuperDARM data. So I'm going to kind of show these two plots together. Now, it doesn't exactly, of course, reproduce. There's some other things to consider, like the fact that the slant range and the group range don't exactly agree. And that could be more to do with the fact that maybe IRI is not quite correctly estimating or producing information about the ionosphere's density profile at the time. But nonetheless, we do get that effect of the echoes disappearing because of the lack of that HF refraction effect there. So these two things are consistent, and it kind of gives an indication that that may be what is occurring during a Steve event, is that, you know, what's coming along with this Steve event is a sudden and very fast change in HF propagation conditions. But it's not, of course, the smoking gun. There are a lot of other things to consider. And I know we're not the first to talk about these type of events. I know Bharat's done a lot of work, and Virginia Tech's done a lot of work looking at the dynamic subauroral region with respect to these kind of dynamic events, and the groups out of Japan have done this a lot too. There are also a lot of things to consider. This is just the first event. The second, this doesn't explain why the echoes reappear and are coincident with the optical signature of Steve in the second event. And there's a lot more to unravel there. And one of the things that I think I will be going in direction of to look at that kind of dynamic event is what the instability mechanism is for initiating these HF irregularities. The temperature gradient instability is something that really comes to mind, and I know has been applied to the region before. And knowing the data from the previous presentations showing both extreme gradients and both extreme temperature gradients, that seems to be a good way to go to. The whole, in a nutshell, of this is that these Steve events have a significant impact and can have a very localized impact on HF radar propagation. And I think it's actually a very, very interesting thing to look at. And I'll leave it at that. Thank you.
Thank you.
There's one question, Bharat, if we have time. I don't know if we do.
We're almost out of time. I can probably ask Carlos's question or maybe your question. I'll quickly pass on your question, and maybe Gareth.
No, I was. There's a question from Daniel Billett here. Essentially, it's and that one we might get through really quickly. Gareth, so the idea was he spotted the backscatter following the arc really closely and wondered if that was the gradient. The electron density dropped so far that you had a nice sharp gradient that was then doing Bragg scatter reflection at HF.
Yeah, that's most likely what it is. I mean, it's such, the SAID or the Steve has such a sharp gradient that it's a nice thing to actually get that scatter off of, which is what my gut tells me what's happening too. And I think Dan's right about that. The thing that kind of bothers me, and I have to look a bit more, is why we don't see that reappearance of the echoes for the first Steve event. And maybe that has to do, it could have to do with the actual overall density of the region. They may be not the same. So you could perhaps get enough of that refraction in the second event to actually see that that Bragg scatter or not. But I don't know why we see it in the second event, but not the first event. And I really need to dissect it a bit more to maybe try and sniff that out.
And the thing that Barat referred to is that Carlos had asked, you know, the 27 September 2017 event was the same one he talked about. He's claimed that's a SAR arc. So the question is, if different processes, same process, you know, we don't really know, I guess.
Yeah, that's a good point, actually.
Great discussion. Gareth, we have some more questions in the chat. So if you want to answer those, there are some questions by Simon Shepherd and Matthew. So thank you. And our next speaker is Megan Gillis. She's from the University of Calgary, and she's going to show us some spectrographic measurements of Steve and the picket fence.
Okay, are you guys able to see my screen?
Yes.
This one here? See my little pointer thing? Okay. So I just wanted to thank everyone for giving me a chance to come here and talk about the spectrographic signature of Steve and the picket fence. It's a fascinating topic, and I like talking about it quite a bit. So what's Steve? As we've heard already from a couple of people, Steve is an optical phenomenon seen in the night sky. It's characterized as a long, narrow purple band of light that resembles an auroral arc with some noticeable differences. And it's these noticeable exceptions from typical aurora that make Steve really interesting and really stand out. So this picture here on the right, or sorry, left, was actually taken by an Alberta aurora chaser named Sherry Grant, and it beautifully illustrates the uniqueness of Steve. So we first off, we see this beautiful, beautiful bright coloring. So this beautiful purple mauve arc, which despite looking like what you'd expect an auroral arc to be, is a distinctly different color. One of the other neat features about Steve is that we tend to find it equatorward of typical diffuse and proton aurora, which we see up here in the north in the green on the left-hand side of the picture. And these are differences from what we would expect from aurora. And then what we don't see in this picture, but what has been talked about quite a bit with other people today, is that satellite observations of Steve have also shown that there's no evidence of auroral precipitation which would be enough to cause Steve's incredibly bright luminosity. So what exactly is Steve? And that's kind of what our question is. So to answer this question, what we did was we turned to spectroscopy. And so for this study, we actually used the newly deployed T-Rex spectrograph. Now this is a high sensitive imaging spectrograph, which is designed to capture the emissions between 400 and 800 nanometers. There are currently 2 of these spectrographs in operation. One of the ones that we use today, or for this study, is in Lucky Lake, Saskatchewan. And the other one is located in Rabbit Lake, Saskatchewan, which is a little bit further north. It operates with a 13-second exposure, and it runs for every 15 seconds. It has a spatial scale of 1 degree elevation per pixel along the slit axis and has a spectral scale of about 0.4 nanometers per pixel. And we absolutely calibrate the instrument so that we're able to get data out in the form of Rayleighs. So looking at the spectra of something like the aurora gives us a lot of information about what chemical composition the aurora has, and that gives us information about altitudes and composition, and also gives us a little bit of clue on its generation mechanisms. So before we look at Steve's spectra, we're just going to see what a typical aurora arc will look like. So on April 20th, 2018, we were lucky enough to actually catch aurora at zenith at Lucky Lake. Now, Lucky Lake is pretty far south. It's about 58 magnetic latitude. So catching aurora down that far south is pretty rare. So we were lucky, we caught some. So in this plot, we have the sample spectra of that aurora. Now, the plot on the right here, it depicts the spectra with luminosity in terms of Rayleigh's per spectral bin as a function of wavelength. And what we see with the spectra is a pretty typical aurora signature. We see well-defined emission lines at green and red, so it's 630 nanometers and 557 or 557.7 nanometers. And these are what's going to give the aurora its distinctive green color and its distinctive red color. We also just see clearly defined N2 plus bands at 427.8 and 470.9 nanometers. And these give aurora a little bit of a blue tinge every now and then. So, and on this particular night, which is really neat, we actually saw proton aurora with this aurora, and we can see that quite clearly in the hydrogen bomber lines here at hydrogen alpha, and then we have the hydrogen beta. So this is pretty standard from what you would expect to see from a textbook auroral emission. So here's another picture taken by one of the Alberta aurora chasers. This is by Chandresh Kedambadi, and it's a beautiful depiction of Steve. So what we want to do is we want to actually see what the spectra we see associated with Steve. Is it auroral? Is it not auroral? What makes it purple? Are we going to be able to actually tell that? And then while we're at it, we want to take a look at the picket fence and see if there's anything interesting there too. So on April 10th, Steve was observed actually by a different set of auroral photographers, Robert Downey and Ryan Salt, at Ness Lake near Prince George, BC. Now, it was simultaneously observed by this T-Rex spectrograph in Lucky Lake, Saskatchewan. And the image on the right is actually from that night that we're going to look at. So they were kind enough to lend us this image. And for those who aren't familiar with Canadian geography, I included a little inset map to show just how far apart these two observing locations were. Just to totally give you that hone in that east-west extent of the size of Steve. So one of the locations was here near Prince George, which is basically above the state of Washington, and it extends all the way across the state of Washington and most of Montana. And then that's just where we stop observations. We might actually extend past this. That's quite a long extent for one of these. So before we actually look at the spectrum of Steve, let's talk about how we process spectrograph data, because this will be important in our interpretation of the results. The spectrograph will actually record a lot of information. Any light that shows up in the sky will be recorded in the data. So this includes ambient air glow, which is a constant emission seen in the night sky, and any light scattered from other bright sources of aurora, particularly to the north towards the south. So in order to determine what part of the spectra is from Steve and what is from other sources, we also look at the spectra directly north and directly south of Steve. Any features in that spectra that are constant to all 3 points, we take to be the background emission. Anything different, we can actually be confident is related to Steve itself. So here's the spectra of Steve. Our background spectra are shown in green and red, and it's important to note that they are very similar to both the north and to the south of Steve. As you can see here, both north and south, they look the same. So the spectra of Steve itself, so the point directly in the middle of Steve, which is this beautiful arc right there, is in blue. And there's two noticeable differences from the background compared to Steve. One of them is that there is a slight enhancement of the red line at 630 nanometers over and above the background emission. And the other interesting thing is this distinct feature with Steve, and that's this line here. So if you see this gap here, it's a continuum emission, which is basically an elevation above the background at all wavelengths. So it resembles closely sort of a broadband continuum, if you will. Now, to get a clearer view, the next slide, we actually subtract off the background that we say is air glow and whatnot, and we actually see just the spectrum of Steve. So this is it's the same plot as before, just with the background subtracted. Now gone are all those bright emission lines, which are associated with other things, not from Steve, and we just see again the beautiful red. So this is again the picture from Robert Downey. And we see a slight enhancement at 630 nanometers, and then this emission feature, so this continuum emission feature. No other emission features that we associate with normal aurora. And just as an inset to show what a black body curve would look like, we just sort of inset ones at different temperatures. So not exactly what we're expecting to see when we started looking at Steve. Interestingly enough, if you actually integrate this luminosity along all wavelengths, you get a brightness for Steve about 6 kilorayleigh over and above the background, which is kind of on par with what people would be able to see in the optics. So this night actually had a picket fence associated with it as well. So we were lucky enough to actually be able to see what the picket fence looked like as well. Same format as before. We're looking at background and the background above and below Steve to get an estimate of our background emission, or sorry, picket fences. And then we actually looked at the picket fence. So same color scheme as before. The red and the green are our background emission, and then the picket fence is blue. What's really unique about this particular one is the only significant enhancement is this pure green emission right here at 55.7. Everywhere else where you expect air glow or any sort of scattered aurora from the north, is the same above the picket fence, below the picket fence. So that is, again, unusual. If we were expecting the picket fence to be more particle emission, similar to what you see in regular aurora, you expect some form of component in the nitrogen band. And we actually don't see any enhancement there. However, we see a massive enhancement of that pure green color. So just in quick summary, again, Steve seems to have a slight enhancement of red, which is interesting, and then an overall broadband continuum. This is highly suggestive that Steve isn't caused by your typical auroral processes. In fact, isn't actually aurora, and it's more likely the result of, ionospheric heating, which is kind of what we've been hearing about SEDS and ZAPs and stuff today. And the picket fence is dominated by that 57.7 nanometer emission. And in that sense, it resembles kind of more like traditional aurora. However, the lacking of the blue component that we would normally expect to see with that green enhancement is distinctly lacking in this particular event. So that's kind of perplexing. And just before I hand it back, I just want to say special thanks to the Alberta Aurora Chasers for their generosity in providing all of the images in this presentation. They are the most incredible group of people, and they never hesitate to lend us their pictures whenever we ask, and it significantly enhances our data. So it's fantastic. So thank you. Yeah, that's it.
Thanks. We have a couple of questions here. Ashton asks, with the slide showing the continuum, do you see the same continuum at different times and different positions in 2D images? In other words, is that continuum the same everywhere in the pixel, at every pixel in the image, or are there variations in the?
There are going to be variations in time. So it's not so like the enhancement, the continuum will enhance in time a little bit, and also from event to event.
But but in the one frame at a single snapshot, he's asking, I think, are there 2D, spatial differences in the continuum, or can you tell?
So the spectrograph is a one-dimensional.
Oh, that's right. This is a spectrograph,
So
right?
If you were actually looking at this in images with different wavelengths, so we've seen Steve with something like FISO, which is filtered to a certain wavelength. You might want to look at Martin Conger's. I believe he might have some like with AUGO or one of those, anything with different wavelengths. I believe you can still see it. Like we've seen this in FISO, RIGO, and spectrograph. So you can see it in different instruments, not just here, but we can't get a 2D image of this.
Okay. Bea, there's one more question probably. Phil Anderson says, there's no blue component in the Steve observation. Where does the purple come from? So
we're thinking that the purple, and actually Jun Liang and Brian might be able to answer this a little better, but the integrated colors of all of them, we're estimating that's what's actually making that purple color. Because otherwise, I mean, when you see green aurora, you have your distinct emission. That's what makes the color. Here we just do not have that. We have a slight purple, or we have that slight enhancement in this event of that red, and that's the only distinct color that we see. Everything else is just, if you integrate over, we're kind of assuming you're going to get purple.
Mm-hmm. Okay.
Thank you, Megan. That was a great talk. Our next speaker is Brian Harding from the University of UC Berkeley, actually, and he's going to show us a photochemical model of Steve. Thank you, Brian.
Okay, thanks. Thanks for having me. So as we've heard, Steve presents a lot of theoretical challenges, how the energy source enters the plasmasphere, how that transmits down to the thermosphere, and finally, how that energy turns into light. So right now, I'd just like to focus on that last question, what is the signal that Steve is giving us? And I'd like to specifically focus on just the upper purple part of Steve. So we've learned a lot observationally, as we just heard. I just want to focus on three things for this talk. One is the altitude. Bill Archer showed in his paper that Steve occurs at above 130 kilometers. That's a bit above most of the normal chemically induced air glow, aurora. although of course not all air glow. If Carlos is right and this Steve continuum actually is a lot higher, I think that's really important information. So Steve exists where particle precipitation doesn't, so it's not classically aurora, and it co-occurs with SAIDs, although SAIDs aren't known to create light. So if it's not aurora, it's not sunlit aurora. These things happen at night. It seems to me to be way too narrow and transient to be heat conduction like the classical SAR arc mechanism. Also, I would think SAR arcs should occur at much higher altitude where the electron temperature can grow very large. But if that's true, Steve should really be a lot redder. And there's not a very strong red line component. So that's another question. Evgeny Mishin had a very interesting point in his paper discussing how the reason Steve might not be redder, even though the electron temperature is so high, might have to do with vibrational nitrogen. So I think that's a very good point. Okay, so adding to the mystery is Megan Gilley's frankly amazing observations of the spectrum of Steve. So here I've just plotted the same data that she published with her paper. So Steve is mostly this continuum emission as we heard. There's a little bit of red line. The combination of that continuum with this red line gives it its purple color. There may or may not be this green line emission. I hadn't seen that plot before that Megan just showed. It seems like she did a more careful background subtraction suggesting there is no green line, but that's also going to be very important to understand. So the point I just want to emphasize is that 95% of the brightness of Steve is actually continuum emission. So that about 5% is the red line. So, these red line cameras from Rigo and Carlos's cameras really are only seeing 5% of Steve. So needless to say, this is unlike any auroral spectrum or airglow spectrum we've seen before. So the fact that it's a continuum, it doesn't appear to have any spectral features that we've been able to identify yet. And given that the T-Rex spectrograph has a 0.4 nanometer resolution, you would expect to see some. That leads us to believe that it's probably not an electronic transition of an atom or a diatomic molecule like N2. This could turn out to be something we've never seen before, but I think we should start with what we know. And what we know is that there is this emission from NO2, the so-called air afterglow emission, that it occurs at a low level in aurora. Interestingly, it also occurs on the RAM surface of the space shuttle. So down here is a picture from the space shuttle. So this is not during re-entry. It's not during when the thrusters are on. This is just normally when it's up at its orbital altitude. And there's this orangish glow that back in the 80s and 90s, they concluded was NO2, the NO2 emission. In fact, there was a Nature paper in 91 that took advantage of a very interesting mistake where they released a bunch of NO out of the payload, and it created a huge enhancement in this emission. So, so there could be a very interesting analogy here. The space shuttle is flying at 7.5 kilometers per second through an oxygen and nitrogen atmosphere. SEDs are going at several kilometers per second through the neutral atmosphere. That there could be a connection here. They think it's this NO2. I should also mention they don't know where all the NO comes from. So there's still an open question here about shuttle glow. Okay, so if you want to try to use NO2, the NO2 continuum emission to explain what Steve is, you run into four major problems right away. The first is just you need kind of a ridiculous amount of nitric oxide if you want to make this reaction happen fast enough to produce 6 kilorayleigh of emission that Megan showed. You need about, depending on how much neutral upwelling you're getting, which is a major question, you probably need somewhere around 10 to the 9th or 10 to the 10th per cc of NO. So this has never been observed, except once. There's this one paper from 50 years ago that it's like a 1.5 or 2 page paper, so there's not a lot of details. They launched a rocket through what I think was an auroral arc and claimed to measure 10 to the 10th NO. So if anybody knows more about this paper, I'd be glad to hear it. Of course, SEDs aren't known to produce NO. So we need a bunch of it. We need it at higher altitude than it really has any right to be. Normally it's around 100 to 120 kilometers. And most importantly, its lifetime is too long. NO is normally it's one of the ways that the thermosphere cools itself off. And it can do this because it has a long chemical lifetime, hours to days. But in order for Steve to be this transient and this dynamic, you need its lifetime to be reduced to a few seconds. So let's look at all the ways you could possibly make NO in the upper atmosphere. So I just grabbed a textbook or a list and showed these. These top 6, there's really no way we could make these work because they involve minor species. There's really a numbers problem here. To get 10 to the 10th NO, even if you turned the entire ionosphere at its densest into NO, it's not enough. Okay, so I claim this, whatever's powering Steve, whatever's powering the NO production needs to involve major species. And that leaves these 2 possible sources. One is an electronically excited state of N2 through collisions with oxygen creates NO. This is known to occur in aurora. But to make this work, you would need to have 6 eV electrons. And as yet, there's no evidence that you could get the 6 eV of electrons. That can easily happen in the aurora or in dayglow, but it's not known here. So if in the future it turns out that there are 6 eV electrons, this pathway should be considered. But for now, I want to focus on this vibrational nitrogen pathway. So, right, the atmosphere normally wants to be oxygen, the O and N2. But if you want to turn it into N and NO, you need about 3 EV. Okay, so on the right here is the potential energy curve for N2. And here, this line is showing the level of the 11th vibrational quantum level of N2. So the point here is you don't need to break apart N2 to create enough NO. You could just give it a little bit of vibrational energy, and then this reaction here will kick off and produce a bunch of NO. Okay, and maybe the major point I want to make in this talk is that this can happen without electrons. We know that ions move very fast in these SAIDs, okay? If you have an ion that's going fast enough, for example, an NO plus moving at 4 kilometers per second is 3 EV. So that can run into an N2 and cause it to become vibrationally excited. And that will kick off the rest. So this is a way to create light without electrons and without photons. So just to put it all together, we know that there's these fast ions in SAIDs. That runs into an N2 here in blue. Becomes vibrationally excited, and the rest is neutral chemistry. Okay, no ionosphere involved at all. So if this holds up, if this idea holds up, it's really a new mechanism to create light in the upper atmosphere, and it could explain Steve. So let's go back to our 4 problems. Again, SAIDs are the only places in the atmosphere where ions reach these velocities. These are extreme. I mean, these are almost orbital velocity. In fact, Carlos just showed an example that was almost escape velocity. Indeed, this 4 kilometer per second threshold that this hypothesis predicts lines up quite well with the survey that that was just shown earlier by Bill Archer. So if you want some more details on the model, check out our paper, but I'll just say that we show that among all of the other chemistry that goes on in the upper atmosphere, if you have about 5 to 10% of N2 in this 11th quantum level, you can get thousands of Rayleighs of emission. Interestingly, this also explains the altitude. 130 kilometers is a special place where the ion gyro frequency equals the ion neutral collision frequency. So below this altitude, the ions are actually retarded by collisions with neutrals and cannot reach E cross B. So they can't reach these fast speeds. So this could explain why it only happens above 130 kilometers. And finally, the lifetime, I'll just mention briefly that this mechanism also produces ample atomic nitrogen. So that actually, if you compute the lifetime of this, that brings the lifetime down to a few seconds. So even though this creates massive amounts of NO, any individual NO particle goes away rather quickly. And allows Steve to be transient, narrow, and dynamic. So this is all encouraging. There are also problems, a few problems with this hypothesis that I'll just point to our paper because I see I'm running low on time. The one, I just think we need much better modeling of this. You know, the set environment is really exotic. It's clearly non-hydrostatic. You have chemical lifetimes approaching, you know, hydrostatic equilibrium lifetimes. So if we get a vibrational kinetic model in with one of these energetic and dynamics models, we might be able to see if this thing really holds up. I'll just point out one easy way to disprove this hypothesis. If anyone has any observations of Steve occurring where the velocity is much less than 4 kilometers per second, say 2 or 3, I think that disproves this, which would be exciting because then we'd be back to square one. Okay, so I'll just leave my conclusions up here and also just want to echo Megan's point saying thanks to the citizen scientists for bringing us this puzzle. It's really been one of the most exciting things I've worked on in my career, so thank you.
Okay, yeah, thanks, Brian. So there's been a couple of questions in the chat. Phil Anderson points out that, you know, it's known that SAIDs produce a lot of NO+, right, from N2 plus O+. And then, of course, the NO+ goes, it recombines and you get N and O. So Liz McDonald says, but she thought that the NO+ recombine more slowly than O+.
No.
But there's Phil Anderson making the comment that corrects that. Okay. So the NO+, I guess we would combine really, really fast.
That's the reason for the chemistry, for the trough. You know?
There you go. Thank you, Evgeny. Okay.
But I just will point out one quick thing that even if you turn the entire ionosphere into NO+, your orders of magnitude too little NO to make enough brightness here. So it's got to be neutral chemistry.
Regarding this vibrational, yeah, actually we also suggested this vibrational excitation mechanism for producing stiff color. Anyway, we did modeling like, my goodness, 30 years ago, 20 years ago?
1989.
1989, yeah. A lot of modeling based on the actually model used for modeling so-called military lasers on the green line, on the NO. Anyway, we found that vibrational excitation alone is not enough to produce significant, more than 10 to 9 particles per cubic centimeter, because there is quenching of the production due to high ion temperature. And basically, Campbell, this Australian guy, improved this modeling, showing that if you include electron-excited electronic levels of N2 into the plate, then you can raise the limit to a few times at least. So that's my comment. But it's very, very, very difficult to make electronic level excited by this even high O+ temperatures. Another comment is that inside SAD channel, you have a lot of suprasormal electrons up to few hundred eV coming from the heated plasma sphere. And that's a fact measured by, by DMSP, for example, or whatever satellite flying in the plasma sphere. So I think, but that's the idea. I like what you proposed, Brian. I think that combining two mechanisms, this ion excitation and suprasormal excitation, will probably be the right way to go.
I agree. If it turns out that there really are a bunch of low energy electrons here, that sort of opens the book for other processes that could be going on, including electronic excitation. Exactly.
Yeah. And by the way, the stronger is said, you see, the stronger the event in the in situ in the plasma sphere and conjugate DMSP, for example, the more suprasormal electrons you have.
Thank you, Brian, for an amazing talk. And I really encourage the discussion to move to the chat because we need to move forward. Thank you so much for all the great comments. Our next speaker is Toshi Nishimura. He's from the Boston University, and he will talk about dynamics of auroral precipitation boundaries associated with STEVE and SAIDs. Thank you, Toshi.
All right, thanks, Bear. So let's see, how can I move this out? Can I make it full screen?
Yes.
I also enjoyed lots of talks and conversations going on in this nice session. And so probably we all now understand that STEVE is associated with intense SAID. We have also looked at swarm high-resolution data to show that there are also waves going on STEVE field lines. They could be lower hybrid waves or kinetic outframe waves that could provide additional heating to the ionosphere. So what I'd like to add in this session is to give more MI coupling perspective to understand the condition of the STEVE occurrence. So one thing I'd like to bring up in here is Bear's statistics paper about STEVE. So she showed pretty nicely that STEVE is exclusively occurring during substorm recovery phase, not in the expansion phase, not in quiet time, not in steady activity. So there has to be something coming with this recovery phase feature. And also STEVE is pretty rare. It's not like all big substorms create STEVE. Only certain substorms make this kind of nice STEVE display. So to understand the condition of STEVE occurrence, we have to solve several problems at the same time. The one is why STEVE is so rare, more specifically, what are the unique MI conditions during substorms with STEVE, and what's the difference from regular substorms without STEVE? And so we have to also understand how these intense SAIDs are forming, why those are happening only for specific events, but not in other events. So to discuss those things, let me bring up some events here. So this is one of the nice STEVE events measured in multiple all-sky cameras. So this is STEVE measured by 4 continuous all-sky cameras of the THEMIS network. So we saw that STEVE extends almost 2,000 kilometers in east-west. Probably this is one of the biggest, the longest STEVE events we have witnessed. And the good thing, or interesting thing in this event, I should say, is that so we see pretty much the full cycle of the STEVE occurrence. First, the substorm onset happened near midnight, shown by this blue line. There's no STEVE yet. These are subauroral proton aurora. But once the substorm feature extends over the Alaska area, then we start to see this STEVE emission. And this substorm looks somewhat different from the regular substorms because the night side aurora is not really confined near pre-midnight region, but the auroral surge quickly propagate far away from midnight, and a lot of auroral intensifications called streamers and surges are going far away from midnight, like 20-hour local time. As soon as the surge gets to Alaska, then we start to see this STEVE feature. Now the surge is still here. It comes with multiple intensifications. Then we see lots of streamers running down, and then we start to see STEVE right at the same longitude. More injections are coming, and then STEVE lasts for 1 hour or so. This is a citizen scientist photograph confirming this is a real STEVE event. So apparently there are some special magnetospheric conditions providing lots of energy to the dusk side, far away from midnight. So that's one feature to keep in mind. And we're going to compare that to another event without STEVE and see what kind of difference we see here. On the left is a kilograms of aurora. So this is also a super kilograms showing how SAID is related to STEVE. So during the expansion phase, we don't see any STEVE feature. There is a subauroral proton aurora. But once the substorm surge come over the Alaska region, which is right here, then we start to see STEVE emission, and then that follows pretty closely over equatorial boundary. And the SAID does the same thing. In Gareth Perry's event, the super echo disappeared. For this particular event, we had pretty good Subaru echo coverage throughout this substorm event. We know the SAID started somewhere around here, and that's right before this intense Steve event has showed up. On the right is just a regular substorm event. There is no Steve going on, although we are looking at pretty much the same strengths of the substorm activity in terms of the measure of the oral electrojet. And our overall location is about the same, around 62 degrees in magnetic latitude. But flow structures are very different. We see latitudinally extended flow structures. So these are known as SAPs without SAID features. And there are also regular substorm events like this. So we are looking at pretty similar oral electrojet. So these are not same seasons, so I have to correct this. And UT is about the same. We're both looking at the Alaska regions, but the magnetospheric conditions are pretty different. So that's probably giving us a pretty good hint of what we need to have to get the Steve occurrence. This is a SUSY perspective of the two events. So we saw in the all-sky camera data that the substorm surge extended far away from midnight for the Steve events. We saw the exact same thing in SUSY UV images. So surge has extended almost to the dusk, and lots of energy is dumped to the Steve occurrence region, which is right around here. And that's very different from a normal substorm of this strength in AL. Substorm surge is normally seen at pre-midnight. Most energy is dumped in the pre-midnight region. So apparently, the way how the magnetospheric energy comes to the dusk side region is very different for the Steve event. So let's look at the MSP and NOAA observations to add more context into this comparison. So this is a two-dimensional illustration of super echoes. So nice SAID flow channels right aligned with this Steve arc. And then we had NOAA and the MSP right crossing over the Steve. For comparison, we're looking at the NOAA and the MSP conjunctions for the substorm without any Steve feature on the right. So there are some discussions in earlier talks what the MSP shows for Steve. So this probably adds good information. So sure, we saw pretty deep trough going on. It's not always like this, but for this particular event, there was a nice trough formation going on. And that was exactly at this intense SAID. And to add some information to Brian Harding's talk, so there's a pretty intense upflow going on. So at least from the plasma perspective, there's a pretty strong vertically upward transport going on, and speed has gone up to 2 kilometers per second in the topside ionosphere. So that's pretty large transport, both horizontally and vertically. And that corresponds to the electron heating region. Another thing to add is that, so there's a broadband electron precipitation going on. So that could be another source of heating. Either this contributes directly to emission or heats the thermosphere and changes composition or transport to help create emission in the thermosphere. The last panel is filter and current. For this particular event, there was a pretty narrowly enhanced downward region 2 going on. So that addresses the earlier filter and current question associated with SAID and Steve. And that's much stronger and narrowly confined compared to the DMSP pass over non-Steve substorm event. And there is no precipitation at all. Let me jump to the flow data. So there is a SAPS flow going on, but notice the scale. This is 1 kilometer per second. So that's just this background broad component we saw for the Steve event as well. So there is no substantial flow peak, and vertical transport is also pretty small. The trough is a lot shallower. Coming back to this middle panel, in the topside F region, we also see the electron heating even without Steve. So that temperature level can be about the same. So the heating is going on for both Steve and non-Steve events. And this could or may not be related to SOX that Carlos has talked about. So the heating may not be directly connected, but strong flows, flow shears, waves, soft precipitation could be the things related to the conditions for giving the special chemical conditions in the thermosphere. Let me quickly talk about the null observations in a similar format. I'm adding one pass right before the Steve occurrence to just give you a perspective. The top panel is the ring current ion precipitation. The bottom panel is the soft electron precipitation. Usually in the dusk side, we see more ions, equator where electrons. There's a ring current. This can be easily explained by a single particle ring current motion. But for Steve event, what's interesting is that this is still during the early recovery phase of substorm, but ions are gone, and trapped ions has retreated back to this latitude, which is pretty close to the equatorial boundary of electron precipitation. So the drive out of region 2 in a subauroral latitude has been confined to a very small area, in this case less than 1 degrees. And that nicely explains why the SAID flow is so confined. There is no region 2 down here. So all the flow has to stream through this narrow region in the low conductance subauroral ionosphere. So that could explain why the narrow SAID forms during Steve, and that is pretty different from the recovery phase of non-Steve event where the ions are still there. So the magnetospheric particle distributions are very different for events with and without Steve. So let me just quickly run before going to the conclusion. We have done also statistical study to confirm that these are not just for one event, but happening for many events that we have identified. Where we have strong SAID, the electron flux is higher than the expansion phase or other substorm events, and pretty sharply dropping ring current ion flux is right on the equator of the electron equatorial boundary. And there's a decent enhancement of downward field line current. There may be a little bit of upward current just forward as well. Electron heating is going on, but that is also there prior to the Steve occurrence. So this may not be the primary factor. And finally, there's pretty strong upflow of kilometer per sec or 4 kilometer per sec. It's a pretty strong transport. So those are the things we have seen by looking at imaging radars and relative satellite observations. The magnetosphere has some unique conditions for Steve events going on. That probably set up the condition to create the chemical reactions that the previous two speakers has talked about. And those can be found more in detail if you wish in this JJR paper just came out. And the bottom line I'd like to bring up is that so pretty strong energy deposition going on in the dusk side ionosphere thermosphere system. And the ring current ion structures is very different, and that could solve both SAID and Steve formation processes at the same time. That's it. Thank you.
Thanks, Toshi. Because of time, I think we're Josh, if you can set up your slide, and I'm going to ask one question from the chat. Liam Kilcommons asked, was DMSP in the Southern Hemisphere conjugate with Steve observations in the Northern Hemisphere?
Yeah. And I don't think that's a bad thing for the subauroral ionosphere. We don't have any parapotential drop going on, and the tail stretching is pretty small. In the tail, that's a pretty difficult question. But by using Cedar model, we get pretty good correspondence.
Right. Okay. There's another question from Brian that maybe you could answer in the chat while Josh goes ahead.
Okay, I'm on.
Yes. Thank you, Josh.
Thanks for having me. This is a really excellent session. It's cutting across this huge swath of the community and people outside our community, or the community of people that talks to each other all the time, at least. So I'm going to look at a pretty focused problem. I'm interested in trying to understand how to organize some of these fine-scale features in the green region that's colloquially called the picket fence, even though sometimes it looks like a really terrible fence. And when we use data from professional scientists, we try to give them attribution. And I'm trying to follow the same thing here on the paper that we're pushing out on this. We've got we're using data from a variety of citizen scientists. I don't know if Neil's still on the call, but he was kind of the inspiration for starting to think about this. Alexei Chernyenkov, Jun Wang, and many of you know Michael Hanakul, who's really doing a lot of great quantitative work in this field. Let's go back to Neil Zeller's measurements and remind ourselves that this really in no way looks like anything that's consistent with a magnetospheric particle precipitation model. You simply can't make features like this, narrow features that are green saturated and produced in this ephemeral way. So the source of a lot of this has to come from some other mechanism, presumably born in the extreme supersonic fields velocities associated with Steve. All right, so one might be inclined to look at a movie like that and declare that it's a turbulent phenomenon. We really can't say very much about it, but as most of you know, you can usually find organization even in turbulent phenomena if you look at it long enough. And so what I was trying
Josh,
to do,
I don't know that your slides are changing. We still got the title slide.
Is that right?
Yep.
Okay, that's weird. Let's see. Resume share. Oh. Bring your shared window to the front. This is I've never seen this before. Let's see, let me try again here.
Okay, now we can see, 4-second exposure.
Excellent. All right. Thank you very much for.
Sorry, I didn't want you to go on too long there.
Yeah, no, that's true. So let's go back and just have a quick reminder of Neil's video of those features, and then I'll move on rather quickly. Okay, so these are features that are a 3.5-second exposure. It's a time lapse. Okay, and this is a 4-second exposure, of course, a single frame. And the kind of features that you see in the box there, one question one might ask is how you, is there any way to reconcile that with the highly dynamic videos that you see in Neil Zeller's image sequences? And this was sort of a second event we started to really look at carefully. Liz and Michael Hanakul had been looking at this already earlier. And what you find are these little streaks that move predominantly horizontal, exactly in the wrong direction. They're moving towards Steve, not along Steve, and they're very narrowly confined in altitude, about a kilometer scale. And this video I like because it is in fact running right now. This is real time at 24 frames per second, 4K. And you'll see in the center there, we can watch little features being formed that move predominantly towards the main Steve channel. And they actually form repeatedly. You can watch another one form behind it. I didn't play the sound for this video, but Alan has a nice narrative of all of this stuff going on, not necessarily about the little streaks, but about the environment in which he's observing this stuff. So we may have an organizational point to start to think about these kind of non-field aligned features that we see in the picket fence region. This is just a summary figure that we opened the paper with, just to show that we observe this sort of thing in a variety of contexts, including ones that where the relationship to field aligned precipitation starts to seem kind of clear. This is from northern, I think, Lake Michigan, Sean Maloney. So let's try and look at someone might ask the question, what's the altitude of these features? Most of us could probably look at this and have a pretty good guess at the altitude based on what we kind of already know about the emissions in this region, but it's very nice to do it quantitatively. And so Michael Hanakul had collected images from Jun Huang and had lined them up really well temporally. And you immediately look at this and say, yeah, this looks sufficient to do triangulation. Let's see, what the heck is going on? There we go. And so in fact, I thought I'd spend maybe 1 minute talking about this because this is a real challenge with using citizen science data to do quantitative analysis. And that is that the cameras are actually not very far apart. They're about 26 kilometers apart. And if you place the object in the sky at the measured observing angles, you get a triangle that looks to scale, like this figure here in the corner. It's a real problem for traditional triangulation. The denominator of the equation you need becomes very small. And so it's really sensitive to errors. And it gets even worse than that because the camera timing may be unreliable. The location may be uncertain. There's differences in sensitivity and color balance, aspect angle to the object that may affect your selection of the points, all of these sorts of things. So it's and these are things we can't really control. And so Michael has worked on this problem quite extensively. And he's taken a very interesting approach, which is, well, we may not know exactly which points line up in the left image to the right, but we can say by the observations that we're moving along a linear trajectory in three-dimensional space. And so we can, there is, you know, through the kind of rules of affine projections, there is a direction vector in three-dimensional space, a unique direction vector that's consistent with these two projections, even if you don't know exactly where the endpoints are, that sort of thing. And so he's applied that approach. I won't go into detail, but he's going to describe it in pretty good detail in a supplement to the paper. And we find that the heights are in the 106 kilometer range or so, which is comforting. We think that this is a lower E region phenomenon. All right, so then one more time back to Neil Zeller's sequence. I'm going to cut out a part of this movie here, show a few frames of it. And we watch these green features marching down towards the horizon. Even though they're small scale features, they're rather blobby like, and they're very ephemeral. They don't live for more than a frame or so. But interestingly, there is one feature that's very reminiscent to the other streak features we observed that is born down here at lower altitudes and actually lives in the image sequence for about 20 seconds. So, you know, about 5 or 6 frames, you can find that feature. So this is again, an interesting point of, to help us organize how to think about some of these features. It's the smallest scale feature in the image. I'm going to show you that it's about 350 meters in width. And it exists as a coherent object for 20 seconds. And it actually follows a curved trajectory in three-dimensional space, which is another interesting point to consider. We can do a little bit of quantitative analysis on that feature. Okay, we can take each one of these little arrows here. You will note that they line up tip to tail. These are the arrows that represent the feature extracted from each of these subsequent images. And we can plot brightnesses along its trajectory. And we find the interesting thing that the width of the feature is roughly similar to the separation of the peaks. And that's exactly what you expect from a drifting point source that's unresolved. So we think this is actually a point-like feature subject to motion blur. And we can play that game in the other direction as well. What I've done here is put a red bar along the local magnetic field line as modeled by Sigonenko. And let's take a cut through that magnetic field line direction as we move from frame to frame. And that is what we're doing here from bottom to top. We start out with just the feature. And then you know, I'm not going to declare any causative connection, but there's a correlation with the formation of a magnetic field aligned feature above it as it moves along its trajectory, which is an interesting thing to consider. And it's consistent with the still images I showed you earlier. That shows that we have a mixture of this feature with conjugate features, field aligned features above it. This suggests some kind of as yet unspecified connection to the magnetic topology, the local magnetic topology. And so this is the second to last slide I'm going to show. This is a summary that tries to expose this connection to magnetic field geometry. This is the one from Alexei Chernenkov, Sean Malone's. Here's this one that I showed, I didn't really talk about much, from Stephen Voss, actually has a curved projection in the image plane. One of those cases where the finite lifetime of the metastable emission that's likely producing this feature gives us an advantage because it tells us a time history. by virtue of its afterglow. Similar thing over here. So, we're obviously still working on this. And some closing remarks, we've determined this is an interesting feature. It's, order hundreds of meters, probably. We don't have a lot of really high resolution measurements of this feature. It's in the lower E region where lots of instabilities coupled together that could produce features that look like this. Curved trajectory, correlation, it has some correlation at least with field line features above it. If I could, I'd like to just make some interesting, to me at least, observational points when we think about things like these green emissions. This is an unknown and unfamiliar projection of the physics, okay? And what I mean by that, it's not a state like an auroral precipitation case where we have a source where we kind of know what the integrated emission should look like and compare it to some other quantity like precipitating energies. Here we have something that we think is produced by probably superthermal electrons locally. That whole process won't become visible until we get a population that turns the lights on. In other words, we need something like substantial population out at 4 EV or so. And more and better calibrated observations are needed to establish its properties for features that are so ephemeral and fine scale as these. It's really going to be the citizen scientists who help us solve these little mysteries. So I've laid down the gauntlet.
So Josh, there's a couple of questions. One of them from a sophomore undergraduate, Vincent Ledvina from North Dakota, who just kind of asked about time exposure, right? Are there things going on even below the exposures that you've got? And are shorter exposures useful, or is the signal going to go down to the point where you just can't see the thing and we have to live with motion blur? I think that's what's under his question.
Yeah, that is a terrific question. And that's the question that people have asked for decades about the Aurora Borealis too. For a while, it seemed that every time we pointed a higher resolution sensor, a higher sensitivity sensor up at the Aurora, we saw smaller scale structures. And I was involved in some of that work too. And of course, that's one of the motivations here. And I would say definitively that we don't know. There's no, if you go back and step through that Neil Zeller sequence, which was 3-second cadence, you'll see features changing substantially from frame to frame, which tells you that you have not resolved it yet. So the answer is, yeah, you need to point a wide field F1 lens with a super electron multiplying CCD up into this phenomenon, and let's see if we see something completely different. I would say the chances are high that we will.
Great.
Thank you so much, Josh. This was an excellent talk and great observations of the picket fence. We have one last speaker and we are running out of time, so I really encourage you to go to the chat and keep the discussion going. So our last speaker is Liz McDonald, and if I am not mistaken, this is part of the work she has been doing with Mike Haneko, and she will present about his historic citizen scientist observations of Steve. Thank you, Liz.
Yes, thank you, Bea. I thank you for the invitation. I'm really glad to be here today. Are you guys seeing the right screen?
Yes, we're seeing your slides. Yep, presenter mode. Yep.
Okay, great. Yeah, I'm really glad to be here today. All the privilege that all of us have to be able to present right at this moment. There's a lot of bad news going on, but on the bright side, we have this opportunity to talk about science, and we have a lot of people all around the world who are interested in this science. And I want to especially acknowledge my collaborator here, Michael Hunnicle, who is up late at night often and joining us from Germany. And I will give him some time to say a few words after I talk about some of our work. So we did publish a paper in a space weather commentary paper in March, showing that kind of bringing it back to citizen science and to older observations here of Steve, and by none other than the very famous Norwegian scientist, Carl Stormer. And turns out that Steve is definitely not new, and he published several papers in multiple languages some of them over 100 years ago, about what really is clearly consistent with what we see Steve as today, to the limits that their technology could observe Steve. And so if you're not familiar with his work, he cataloged aurora, all kinds of aurora for multiple solar cycles. And he was the first person, I believe, to really triangulate with photographs and with a deliberate network of simultaneous observations around Norway, especially, the height of the aurora. And so he captured a few observations of something unusual and described it. It's all very consistent with Steve. Feeble homogeneous arcs of great altitude, where it's definitely notable that the great altitude really stuck out to him and his collaborators right away. So I have a few more thoughts on, what can history teach us here? So one, we really want to write papers that are going to be readable in 100 years. There's also some interesting points about he did not observe Steve very often. And why was that? It's possible that, I don't think we really know, but it is possible that there's some longitudinal preference for these observations. That's something that we have not discussed here today, but also requires further observations. A couple more basic points, just to remind people that Steve is very much colorless to the naked eye. Looks quite a bit like aurora, although quite a bit further south or away from the pole. And the aurora itself often is quite colorless and fairly weak to the naked eye. Carl Sturmer had spectrographs and different types of film, and he definitely noted that initially he thought, this looks like aurora, I'm expecting it to be green. And it was not green at all in his spectrograph. So he did not, it was limited what he could observe, but he definitely reported that it was an atypical spectra. I also want to point out that many of us did literature searches on this before our initial papers and other publications, and we all missed this. So it's just good to keep it in mind that there's pre-space age extensive observations of aurora and all different types of aurora, some of the rarer types that we're now interested in the subauroral zone. I don't believe, Michael will correct me if I'm wrong, but I don't believe he described the picket fence, and really with the naked eye, mostly you can't really see the picket fence very distinctly. It's also good to point out that now with our cameras, our modern cameras, and some of the extremely beautiful photos that people have taken of the picket fence, you might think that that's always there, whereas it's actually quite transient. And so it's interesting to think about how what we now see and the many pictures that we see, how all of this can affect our own processing and thinking about the observations, and how important it is to be quantitative and to collect as many observations as we can so we can truly get better statistics on how where it is observed and how frequent it is observed. I also want to point out there are many different triangulation techniques. In the lower right here, you can actually see the technique that was used at the time of projectors, projecting glass plates of photographs onto the wall and then calculating the angles. As Josh just mentioned, there are many different new techniques involving triangulation today, and Michael has really done a lot of great work on this. And so it's important for us to take into account with our current technologies and some of those limitations, how to do this as well as we can and as well as other people around the world, including citizen scientists, might want to triangulate images. Past observers really might have understood height, or what I mean by that is where in the sky the aurora was, because they were out there seeing it and they knew, you know, their constellations and how fast it was moving. And it's really amazing when you look at some of these older observations, the sketches of these arcs and the precision with which they were able to describe the behavior, you know, with the technology that they had. Michael also has done an extensive literature review on the historical observations and on modern citizen science observations as well. I'll let him talk more about that. Steve Mendy actually told me at AGU, you know, it's comforting that Steve is not totally new. It did not just completely pop out of nowhere. And of course, those of us involved with the citizen science side, even before it was called Steve, of course, it was called a proton arc, and there were many observations all around the world. We've not claimed that Steve is entirely new, but really the identification with the SAID is what's new, and the picket fence part is what's especially new as well. And so just in closing, kind of citizen science has helped make auroral discoveries for more than 100 years. Carl Stormer also included networks of people. He got on the radio and asked people if they had seen the aurora and to send him reports and that sort of thing. And there are other examples in our field as well. I'm gonna end there and give Michael a couple of minutes to add more.
Yes, hello, thank you for introducing me to the community. Just a few words to my work on Steve. So as Liz said, yeah, I found historical observations made by Stormer, reported first in very detail in 1935. And after I found that paper, I go deeper into literature research and found many candidates for historical observations. I think up to date, I have more than 100 likely and very likely observations reported, which goes back to the beginning of the 18th century. What I also did is I searched for observations posted by citizen scientists for the 21st century, build a database, including time, geomagnetic data, and this database includes up to 150 days with time. I also correlate all observations reported by amateur observers for the 21st century I found with geomagnetic data. So I connect them with geomagnetic storm phases, calculate the monthly reporting rates, the yearly reporting rates, and so on. And yeah, as Liz also said before, I developed a triangulation algorithm that allows me to calculate heights for specific discrete elements in Steve, and also especially picket fences. Where I also start to calculate our drift speeds for picket fences, and for the event I analyzed in detail, shown here, I come to speeds very similar to those reported by Archer in the range of 150 to 200 meters per second. And I was also able for one event to measure the drift speed of discrete structures in the whitish part of Steve in the range of 10 kilometers per second. Yeah, and yeah, I think this is more or less most of what I did in the past, and yeah, it's a pleasure to me to serve the community with my results, and yeah, hope that the databases I built are helpful to search for conjugate observations. I forgot to mention that I also identify 16 days, I think, for which I found observations from both hemispheres. In 3 cases with a time delay of less than an hour. So I think these 3 events are very likely candidates for congregate observations, but more detailed analysis is of course needed to see if they will be congregate. Okay, that's all.
So, Bea, there is one question from Carlos. You mentioned that he was wondering if Steve's were already observed during the recovery phase of a storm. And I think you just said that that's not necessarily the case. And he was wondering if you could elaborate on that.
Steve can in general be seen in every phase, but mainly in the recovery phase, as far as I can say based on the observation. So I have to rely on the reported observation times, and there's of course some uncertainty because more or less all observers do not use calibrated camera time, but if you have more than one observations, you can be sure then that the time is more or less correct. So yeah, I think I don't have the time to go in all the details for the to show results for the correlation with the magnetic storms. But if anyone's interested in my analysis, I can send detailed information.
Yeah, Michael, I would say that based on the comments, there's some considerable interest in that. So I would put that high on your list as something to look at. Bea, you had a question, I think.
Yeah, I was asking if you observe any morphological differences for Steve events observed during different substorm phases.
So I did not analyze correlations with substorm phases so far, only with geomagnetic storm phases. So I looked for the main phase, recovery phase, and so on, but not for substorm phases, just because of lack of time. So I do all my analysis in my free time and my normal life. I'm a laser physicist, so I'm very limited in my time. So because of that, so far I did not do that.
Michael has also very generously published the database of observations with a huge number of events on the Open Science Framework and some of so that's a good place to find some of that and collaborate with him as well.
Great, and that answers a question that Brian had put in the chat too, so fantastic. That's a lot of work, by the way, Michael, for something that you're only doing here and there. Trust me.
Very impressive.
Trust him, definitely.
Yeah.
Trust him. He's
Wow.
done a really, really great and very detailed job with all of this.
I heartily agree just from seeing that presentation. It's amazing. Okay, Bea, I think we got most of what was going on in the chat there.
Yeah. And that was our last talk. It was a fantastic session. We had 136 people attending between Zoom and YouTube. So thank you everyone for joining, and thank you to the speakers for these amazing discussions and talks. Thank you, everyone.
Thanks, Bea, and everyone.
Thank you.
Thanks. This was great.
Thanks, Bea.
Bye.
Thank you all.
Thank you, Bea.
Goodbye. Thank you.